let's not worry about it. So you don't want to mention anything about the app?
I don't see it anymore, the questions.
Oh. They activate it sometime during the talk, I think.
I think that's only for the big room, I suspect.
Oh. Yeah, it's not here. Ah. Yesterday it had it.
Yeah, it was here. It's
But
not
it was
there anymore.
Okay. Fine.
Ask how many posters they have uploaded.
There's only two, I think. Good. Good to see you.
So last SnT we did it, huh?
We did?
Session. We had a session.
Oh, I had to. That's right. Yeah. I'm back. Yeah. I'm well. I'm well. Yeah.
Hi, Terry.
Hi. So there are only 3 posters uploaded.
Yeah.
We don't have to worry too much about it.
Then we can have 5 minutes. We will go to the post.
Wait another minute.
It's a pity people missed the fantastic presentation of the Director General of Forecasting for Meteo Canada. It was amazing what he shows.
Good afternoon, and welcome to session T 4.4 on performance of the full verification system. We have 3 talks this morning, and the first talk is called the third ATM-Challenge 2019 by Christian Maurer. I'm going to have the time on here if you care, so I'll start the time.
Yeah, well, good afternoon. So I would like to talk about the design of the third ATM Challenge 2019. I will present the scenario and I will give a brief introduction regarding practical guidelines. First of all, I also have to apologize. In the abstract, it says that I will present first results, but as it turned out, designing an ATM challenge is a challenge in itself. Of course, a comprehensive work like this cannot be done alone, so I would like to acknowledge all my colleagues listed here on the first slide, especially Jolanta Kuzmicik-Micholec, because she has done really very comprehensive evaluations of the so-called dry run, so when we tested how things look like. Yeah, then the second slide is about the history of ATM challenges. So there was a first and a second ATM challenge. I do not want to go into details. There are, I think, nice publications, one led by P.W. Esslinger and another one led by myself. So these publications very nicely summarize the 2 challenges. Maybe just to state that the purpose was to ascertain the level of agreement one can achieve between real IMS measurements and those simulated using only the stack release data ATM. So this was the purpose which was stated in advance. So yeah, talking about the third ATM challenge, what is our scenario? So the scenario is 6 months of atmospheric dispersion simulations, June to November 2014, in order to cover seasonal variations and really yield robust statistics. And we are working with 4 target stations, which are frequently hit by known emitters in the northern hemisphere within this time frame. So this is Charlottesville, Schauinsland, Stockholm, and St. John's. And we are dealing with two kinds of sources. So first of all, there are the main sources. This means daily releases from the medical isotope production facilities, Shock River Laboratories, CRL, and IRE. This means l'Institut National des Radioéléments. And then we have, as a second item, minor sources, or we plan to have minor sources. And this means daily NPP and research reactor releases, also in the Northern Hemisphere, and also annual releases from some minor facilities, minor MIPFs. This means Mallinckrodt and NIR, but also from the Karpov Institute. Yeah, and the coordination team, as I said, this is a multinational effort. The coordination team consists of ZAMG, so I'm representative of ZAMG, of course CTPTO, IDC, but also CMC and NOAA said they would be willing to help, especially with the evaluation. And here our clear aim is that we have a first time step in the transition from merely scientific case studies to the practical use of forecasting radioxenon background at selected IMS stations. And therefore we want to include as many emitters and really end up with statistic robust results. Yeah, here we have an overview of emitters and the receptors. So we have here the big red boxes. These are our two main emitters. Then we have the minor emitters I mentioned. These are the orange boxes. And then you see all these green dots, which are the nuclear power plants involved, so 173. As it is written here. Yeah, and the blue stars denote our target IMS stations. Yeah, what is a pending need for this new ATM challenge? We clearly want to prescribe more model setup parameters because we clearly have to enhance comparability on one side, but also diversity on the other. So for the previous challenge, emission resolutions in terms of time were prescribed to the participants for the blind test approach. However, there was critics, and I think justified critics, of comparing non-uniform spatial resolutions concerning the model output. So parameters in this new challenge clearly should be harmonized and controlled as much as possible. And to see how well this could be achieved, we sent out a purpose to possible participants, a questionnaire. For this purpose, we sent out a questionnaire to possible participants in October 2017 to check what could be achieved, and we gladly received 11 answers. Yeah, so what are the parameters in question and what is the feedback received? So the dispersion model, I think we cannot say much. This clearly cannot be described. With the methodological input data, it somehow looks different. It may be prescribed for some participants if input data pools are provided. Because what we want really to achieve is that not all FlexPod users, as it was the case in the previous challenge, use eSIM-WF input, and not all high-split users use NCEP input, because this makes it then very difficult or even impossible to discriminate between the effect of the model and the Meteo data. Consequently, also the spatial resolution may be prescribed. Temporal resolution, here we can state that the maximum possible for everybody is 3-hourly resolution. Concerning the model output, maximum spatial resolution for everybody is 0.5 degree, but I think this is okay because we are dealing with a hemispheric simulation. What can we say about temporal resolution? Here, maximum possible for everybody is 1 hour, according to the questionnaire. However, this does not seem to be a critical parameter because we have to be aware of the large averaging time applied when comparing model simulations with IMS data. Vertical resolution, here we can state that the surface output layer could be prescribed to some participants. Simulation direction should not matter, so participants can use forward or backward as they like. What about emission resolution? So temporal resolution, participants said that a maximum of 1 hour should be possible for everybody. And we also should bear in mind that results for lower resolutions can be produced in a post-processing step simply by averaging. However, the primary focus will be clearly on daily emission resolution. And in this respect, I also recommend checking a poster, so poster P10 under topic 4.4, where it is somehow demonstrated why it may be enough to focus on daily resolution. Yeah, and participants also claimed that they would be able to include all the sources, so this means also the nuclear power plants. So number of particles released in internal model time step may be prescribed, but this largely depends on the organization's capabilities. Parameterizations may also be prescribed, and we have to bear in mind that diversity is needed all the more as the ensemble of model runs will not likely be optimal diverse due to the two dominating methodology model combinations. And finally, simulation length, well, 6 months should be feasible for nearly all of the participants, but this is not a must, but 3 months is a must in order to perform the necessary evaluation. Yeah, one very important thing is the ensemble approach we want to deal with, and here we are envisioning a cooperation with the Joint Research Center in ISPRA, Italy, because what one should bear in mind, averaging all model runs together in a multi-model exercise where similar model errors may be encountered is not appropriate. We need to select an optimum ensemble combination, and an optimum ensemble combination, as Stefano Galmarini from GRC showed, an optimum ensemble combination per station and per season can be trained with sufficient data, and this is the reason why we are hoping to have a simulation period of 6 months. And finally, what should be stated is that an optimum ensemble can indeed outperform the best individual ensemble member. And for this, you really you need a good balance between accuracy and diversity in your ensemble. Here is an example from the second ATM-Challenge. I mean, due to the lack of diversity in our ensemble, the feature we are looking for is not very pronounced, but you can see here, so in the rank, so the optimum is not reached if you average together all the ensemble members, but there is an optimum at around 5 to 6 ensemble members. Yeah, finally, hints to bear in mind for the computationally intensive simulations. So, of course, you can use particle aging. There is no need to track all the emissions until the simulation ends, especially because Xenon 133 has a half-life of just 5 days. Then you could split the simulation period in 2 chunks of equal length and define an overlap period according to particle aging. So this is illustrated here. Then what also can be done is perform 2 separate runs per simulation subperiod for the main and the minor emitters, because for the main emitters, participants should follow a unit emission approach, and the emissions need to be tracked individually, where the minor emitters can be lumped together, so participants will receive the input data or the emission data right at the beginning. They can lump all the contributions together, and there is no need to track the emissions individually. They just have to give output for all minor emitters. And then we will add this to the scaled values which will be produced for the 2 medical isotope production facilities. Yeah, but this inclusion of the minor sources is optimal, so if a participant does not manage, it can also be left out. Yeah, and so I slowly will come to an end, and here at the end I'm now showing some interesting plots regarding the involved stations. So what is the situation within the months in 2014, and here we see a clear difference between the European stations involved and the 2 North American stations involved. So for the European station, you clearly have a variation from month to month in terms of contribution, and especially interesting is November 2014. I was very puzzled at the beginning when looking at this, but then I checked the pressure charts, and there's a persistent southerly wind direction, which means that all the emissions from Fleurus or ERE were transported away from station Schauinsland, and therefore the reactor emissions gain much more importance. For the North American station, the situation is completely different. You see that CRL emissions are dominating over all months, but this also has to be seen under the light of total emissions from ERA and IRE and CRL, so there is nearly one order of magnitude difference in emissions. So let me come to the last slide. So what is the Persued timeline for the third ATM challenge? So we really would like to start very soon, but yeah, I cannot unfortunately state a specific month. I can only state that yeah, it will happen in 2019. But participants can already start the procedure necessary for a WIDEC agreement if they want to receive all the emission data and also the IMS measurement data. Yeah, once the challenge is officially launched, participants should inform the scenario team about the planned model setup within 2 weeks, and then we would like to discuss with participants which elements of the setup can be prescribed. Then participants will have 2 weeks, as requested in some of the questionnaires, to complete their runs. And as I said before, so all the emission data and the IMS measurement data are supplied to participants in case they sign a WIDEC agreement. Yeah, and results are hopefully to be shown at the next WASMIP workshop, I think, which will take place next spring. So, yeah, last remark is if you have any suggestions related to the design of the third ATM challenge, please state them right now. And with this, I would like to thank you for your attention.
Thank you very much. We have time for questions, and please use a microphone. Any questions? How about some suggestions, as he was asking for? Any input at this point?
Maybe everybody's satisfied.
Yeah.
I don't know.
Do you have a question? Okay, thank you very much. So I failed to introduce my co-convener, Thierry Heritier from CTBT, and I'm Tim Ahern from IRIS. And I apologize, but the room is fuller now than when we started. So we can start the second talk now. And it's the International Monitoring Systems Detection and Screening Capability in Australia, given by Tanya Page from Geosciences Australia.
Oh, it works. Hello, everyone. My name is Tanya. Thank you all for coming here. You will excuse me as I sleepwalk through the clicker. It's well past bedtime where I'm from. Okay, so today I'll be talking about the IMS's detection and screening capability in Australia. I'll focus on the Global Association and NetVisa algorithms by comparing the bulletins that they produce, so that's CEL3 and VCEL3 respectively. And I will compare those to Australia's National Bulletin and the Late Event Bulletin, the LEB. I chose to compare them to LEB rather than Reviewed Event Bulletin, REB, because the LEB is curated by human analysts, and it gives me a good idea of what these highly trained analysts consider to be an event. So, as we know, every automatically detected event that comes through CEL3 needs to be closely examined by a human before the LEB and its cousin, the REB, can be released. Nearly half of all of these events are thrown out or completely rebuilt using detections that have been erroneously assigned to other events. And for over a year now, the CTBT analysts have had access to the so-called Visa button, which allows them to access all the automatically detected events by the NetVisa algorithm. And this algorithm uses probabilistic inference to work out a seismic bulletin which best explains a set of arrivals at primary and auxiliary IMS stations. One of its many goals is to produce fewer false events without missing an event, and to produce more events that will pass the analyst's scrutiny. So further down the line, the overall goal is to reduce the human analyst's workload. NetVisa contains prior probability distribution functions, or simply priors, that provide instructions for evaluating a probability of an event and a set of arrivals. For the event location prior, which is something that we'll be sort of focusing here as well, is based on tectonic geography of the Earth, which simply means more events will exist where there's higher seismicity. And on top of that one, there's a small uniform prior added everywhere to allow for explosions to happen anywhere in the globe. The NetVisa algorithm is trained, and the LEB, so the Analyst Curated Bulletin, is used as the ground truth for event location prior. And so the questions that we'll be asking here is how well are global association algorithm that eventually produces the CEL3 bulletin and the NetVisa algorithm performing in Australia? Particularly, can Visa really reduce the human analyst's workload? Which events are captured? Are they all? If not, how many are there? So we had a look at all the bulletins released by CTBTO, and I promise you these are actually really nice colours, but I bet you can't see them because of the light. So we looked at about 7 months of last year. So on the left-hand side, we've got Geoscience Australia's National Earthquake Alert Centre Bulletin, and in the middle we've got CEL3 with over 1,000 events in this area and in this time period. VCEL3 with just over 300 events, and LEB and IRB each have under 200 events. Since we'll be focusing on CEL3 and VCEL3 and comparing those to Australia's National Bulletin and the LEB is reproduced here on the right side with red triangles showing the primary IMS stations. So the triangles on the top are primary IMS arrays, Warramunga and Alice Springs. And down the bottom is Stevens Creek, and then in green are all the auxiliary IMS stations in this area, and you can see there's not a lot of them for a pretty big area. All the events that are plotted as stars have screening scores less than 0, which means that they have not been screened out and appear explosion-like, if you wish. For whatever reason, everything else has been screened out. We compared all of these bulletins in the middle to the bulletin that you see on the left, which is Australia's National Bulletin. And we used certain criteria to do so. So we separated all the events in Australia's National Bulletin into those that have local magnitude in a range of 3 to 4, and those that have local magnitude in a range 4 and above. So everything that's below magnitude 3 we don't look at, and most events in Australia are. We then used 2 sets of location and time criteria. The relaxed criteria demand that the epicenter distance between the 2 compared events be no more than 200 kilometres, and that the origin time be within 60 seconds of each other. And with the strict criteria, we keep the distance requirement but demand that the origin time be within 10 seconds of each other. And this coloured table shows the number of events matched with Australia's National Bulletin for every CTBTO's bulletin in rows and for each of the criterion in columns. And the darker the colour, the more events it matched. So you can see that for the relaxed criteria in the magnitude range 3 to 4, LEB leads this with 34 matched events, followed by Visa's bulletin at 28, and then CEL3 in this case and IRB have similar numbers at 21 and 22. If we tighten the criteria for the same magnitude range, so that's third column, you can see that these numbers reduce significantly, and more importantly for us, Visa matches double the number of events than CEL3. We have 115 events in Australia in this magnitude range, and we associate the differences in these numbers to relatively poor estimates of location and magnitude resulting from using IMS stations only in this sparsely covered region. More often than not, the stations that form these events that have matched here are only primary IMS stations, and auxiliaries are rarely used. We have 25 events in Australia and the surrounding region in magnitude 4+ range, so we can see for relaxed criteria, so the second column, CTBTO bulletins are complete, so that's really good news. And Visa is actually working overtime and matched 2 of its events with one and the same event on the Antarctic Ridge. Again, for strict criteria, these numbers reduce quite significantly. We proceeded by taking our relaxed location and time criteria to now compare the CEL3 and VCEL3 bulletins to see whether VCEL3 or whether Visa essentially captures the events that already exist in CEL3 and are created by the GA algorithm. So in the middle here, we have the entire VCEL3 bulletin for this area and time period. Highlighted in yellow are all the events that have matched with an event in cell 3 according to our relaxed criteria. And on the left-hand side is the entire LEB bulletin for this same time period, and highlighted in blue are all the events that specifically come from cell 3 based on their EVIDs. On the right-hand side, these two highlighted subsets of events are just overlaid on top of each other. And this gives us a visual representation of whether the VCEL3 events that at this stage are not even reviewed by analysts, whether they cover the cell 3 events that have been reviewed and deemed good enough to go into LEB. And you can see that that is essentially the case. So with a little effort from the analysts, or rather just reviewing these events, the visa could already form a very similar LEB, or potentially maybe even the same. In the areas where we don't have visa events covering the ones in LEB, we can see in VCEL Bulletin there exist actually candidate events, and it simply may be that these events haven't matched according to our subjective relaxed criteria. And also analysts look at cell 3 before they look at VCEL 3. So you can see candidate events everywhere. So if we go back to our little table, and we have 34 confirmed events in LEB that have matched with something in Australia's National Bulletin, and if you assume for a second that only cell 3 or only VCEL 3 are contributing to that, then cell 3 would contribute 21 events, and VCEL 3 would contribute 28 events. So to me, that sounds like a pretty similar performance, with visa potentially performing slightly better. However, we saw at the start, cell 3 produces over 1,000 events in this time period, and VCEL 3 does only over 300. So for a very similar end result, which is the LEB as we see it here, visa could already reduce the analyst's workload simply because they would have to sift through fewer events. So the question is now, how much does visa actually contribute to LEB in this region? It appears not much. Okay, so the color codes here are the same on the map and in the bubble chart. There's a total of 194 events in LEB. Only 9 of them come directly from visa. They're shown in magenta on the map. I don't know if I have the... Anyway, so there's 9 of them on the map. I'm not going to point them out now because they're hard to see in this light. But what you probably can see is that there's a lot of events colored green. And those are all that have been manually created by the analysts. And there's a lot of them. There's 58 of them. That's nearly half of what's already coming through cell 3. And why is that? Why are analysts still doing a lot of work when they have 2 detection algorithms that should be doing that work for them? Are they potentially not performing well in certain regions? So we'll have a look. We'll have a look at the Southern Ocean here and see what's going on there. Mining region of Bowen Basin in Queensland, and Pilbara region in Western Australia. So here's the situation in Southern Ocean. That's the island of Tasmania in the upper right corner. Again, the colours are the same on the map and in the bar plot. They show different contributions to LEB, so cell 3 analysts and visa, and they also show different event types in Australia's National Bulletin. Everything that you see in light beige is an earthquake in Australia's National Bulletin, and there are 2 grey dots on the island of Tasmania that are 2 mine blasts. What you can see here is that the IMS actually detects a lot more events than Australia's Earthquake Alert Centre. Possible reason for that is that the primary IMS arrays, Alice Springs and Warramunga, are unfortunately at the moment not used as arrays, but rather as individual stations. So that makes it really hard to locate events in this area that are lower than magnitude 5. Another thing that you can see is that, for example, right there, you have a lot of events of all the colours. So we have something that's coming from cell 3, from the analysts, from visa. They're almost literally plot on top of one another. And the question is, why are the analysts still needing to do all this work there? Why are these 2 algorithms not finding those particular events? We have a similar situation in the mining region of Bowen Basin in Queensland. There's 1 beige dot at the top of the map. That's the only earthquake that Australia has recorded there. We have nearly 50 mine blasts. We have a decent number of events in LEB. But you can see from the bar plot that the analysts are manually creating more events than CEL and VISA combined. Again, all in the same region. Why is that? And most alarming probably is the Pilbara region in Western Australia, where we have all of 2 earthquakes recorded, hundreds of mine blasts, only 4 events in LEB, all 4 manually created by the analysts. So CEL and VISA have contributed exactly nothing to this area. Again, why is that? If the analyst's workload is something that is a standard that we're striving towards, then that standard is not being met here. So, in conclusion, we have examined all of the bulletins released for about 7 months of last year. We focused on CEL3 and VCEL3, and we compared them to Australia's national bulletin and the LEB. We saw that CEL3 produces 4 times as many events in this region and time period than VCEL3. And we have also shown that basically VISA and GA are performing pretty similarly, with VISA potentially marginally better. However, human analysts are still contributing a significant number of events to the LEB, and we need to address why that is before net VISA could potentially be operationalized, and before we need to tune it, and we need to understand it better before it can reduce the analyst's workload. For Pilbara, I can offer some suggestions as to maybe why the net VISA is not potentially performing really well there. I haven't tested these, so I don't know, but it's possible that, as I said at the start, net VISA needs to be trained, and it's trained on LEB as the ground truth. If the LEB doesn't have events to begin with in that area, then the algorithm will learn that there are no events there. The small uniform prior that you have on top of the event location prior, that's the tonic one, seems to be rather ineffective in this area. It is also possible that the primary arrays Alice Springs and Warramunga are not well tuned to the high frequency content of the West Australian earthquakes and events in that region. So we suggest that VISA should be trained on local NDC database and not LEB. And we have one running at the moment at Geoscience Australia, and hopefully sometimes next year we can report on how it performs when it's trained on local database. So that's it. Thank you.
You have time for at least one question. Can you use a microphone?
Thanks. Congratulations. Very
Thank you.
excellent work. And actually, it's our day-to-day work at the IDC. And there are many questions here. But regarding the magnitude, I saw that there are some parts where you were assessing 3 to 4 magnitude.
Mm-hmm.
I think that probably would be better to be more granularity there, because there are some conditions for the CEL3 to exist, which is the detection by 3 primaries. So
Yes.
on that aspect, I'm not sure how did you manage the comparison with the...
If I had more time, I can show you later if you like which events have matched. So I have some maps that show exactly what matched where. So you can come and see me, please, later. I will gladly show you. You would be surprised. The events that are in CEL3 and VCEL3 tend to be on that magnitude. Sometimes local, not always MB. So, yep.
Okay. Thank you very much.
Thank you.
Wait, is it a quick question? Okay.
Okay.
One more.
Did you check the events that were created by the analyst? Is it that the analyst really picked the detection, or it's only that he associated detection that were already in the detection list of the IDC?
So I actually am not quite sure how to check that, because so to look into CEL3, I need to log on to archival database, and it's actually quite hard picking through it and figuring out what came from where. So when I say that they have been manually created by the analysts, it means that they don't appear anywhere else. They're not in CEL3, they're not in VCEL3. Whether the analysts have literally put a pick in there or associated a different detection, I'm not sure. I don't know how that works. But so some of those events are also created using some of the infrasound stations, especially the one in New Caledonia for, say, Queensland. regions.
Okay, thank you. I think we should move on to the next talk.
Thank
Thanks
you.
very much. And our next talk is near real-time monitoring of the IMS event detection capability by Tormod Caverna.
Well, good afternoon, everybody, and welcome to this presentation. I'm going to talk about how we, quantitatively and in real time, near real time, can assess the detection capability of the seismic component of the IMS network. This is important to place confidence in the performance of the verification system, and it's an information that I think most of you would like to know when you are going to do global monitoring. There has been several studies on the capabilities of different stations, how they perform with respect to the detection capability. This is an example for the Arcus station, where we analyzed the IMS Reviewed Event Bulletin and came up with a distribution of capabilities to detect events. And we see that for Northern Europe, the capability is 3 or lower, and then, of course, you have areas of Central Asia or Asia which also have a good capability to detect events. But, of course, as expected by the attenuation curves, you have more distant areas where you have quite low detection capability. Similarly, if you go to the Warramunga array that was mentioned in the previous talk, you have a good capability to estimate or to detect events in the southern hemisphere. So what has been done is to combine these capability maps for different stations to come up with an average global capability map for the IMS primary seismic network. And this is using the criteria in the operations manual of the IDC. You can calculate the 90% probability of detecting an event at 3 or more stations. So we see here that we have, for the northern hemisphere, we are ranging between 3.4 and 3.1 or in the capability, and a lower for the southern hemisphere, ranging between 3.6, 3.7. So this is the average properties of the IMS system. But in reality, we know that the capability is time varying. This is an example from 2011 where we have calculated the amplitude averages in 1-minute chunks within the detection frequency band for different arrays. And on the horizontal scale axis, you have the day of the year, so it's the period from January to October 2011. On the amplitude scale, you have the log amplitude, which scales with the magnitude of the event. So you see that during winter season, you stay with the numbers. These are just the count numbers, but the relative scale is important here, that you have a change in log amplitude levels of almost 1 magnitude unit between the winter season and the summer season. So if you then see here, this is a well-known fact where the surface waves on the nearby lake is creating a lot of noise and increasing noise levels. Similarly, we find from the V&A station in Antarctica higher noise levels during the local summer season, which probably is due to the open seas and the wave actions. And as you see, the difference between minus 0.5 and 0.5 is 1 magnitude unit lower detection capability for that station. Similarly, we had the Tohoku earthquake in 2011, where you have a significant rise in the amplitude levels for this, at least for the YKA stations. And in addition, you have local signals at stations that influence the capability of your network. Another interesting observation was when doing similar type of analysis with 1-minute averages for the Chiang Mai station in Thailand. You see this rugged pattern, it's undulations. And in investigating in more detail the temporal behavior, you see that there is a significant difference in noise levels between day and night at these stations. So we're interpreting at least half a magnitude unit lowered capability during the time period 0 to 12 UTC, which translates probably to daytime in Thailand. So we know that there are several factors that influence the capabilities. You said temporal variability of background noise, local signals, coda from large earthquakes, stations are out, communication gaps, data processing failures. All these things influence the capability of your network. And we have worked with the IDC, or we have been implementing currently, or it has been running for some time, what we call the threshold monitoring system that provides the IDC with hourly averages and worst case estimates of the global detection capability, which take into account these factors by processing real data as they arrive. And the results, this you can find on the secure web portal of the IDC. You find the 1 hour average detection capability for the IMS network for a given time period. So this is updated regularly. However, and of course this provides confidence in the performance of the network, but we are of the opinion that this method is not fully exploited, and that can be further improvements and help to the state signatories to further develop this method. So I will give some examples here. The old implementation of this method was based on a rather coarse grid, and that was a limitation by the computing power. This is now significantly developed over the last years, and for instance, we have made an experiment now with a much 1D grid system. I come back to that. You can also calculate these capability maps with much denser time resolution. Instead of having 1 hour averages, you can calculate them as dense as you like. This is an example for a 5-second update. And what you see here is the capability map for 5:07 on the 25th of February last year. So you see this is the capability map that you get out for that time instance. I will also illustrate now in how this kind of capability map will change, maybe during a 1 hour period, during a large earthquake in Papua New Guinea that happened on that day. So you just follow this. This is an animation, and you start out like this, and the clock, you just follow the clock, 7:15. The event will come around 7:40 or 5:40, and then you see, to start out with, the capability is kind of pretty constant, but as you approach the time of the event, you will see that the capability of your network is starting to deteriorate. And then you get some side lobe effects, and then suddenly you have the event in Papua New Guinea, and you see that the detection capability of your network is significantly deteriorated during the time period after the event. So for this 7.5 event, this lower capability lasts for about 1 hour until it returns back to normal. So this is one of the things that these sort of measurements can contribute to kind of highlight instances when you have a lower capability, and also to quantify the numbers, how this develop. In addition, having a denser global grid system, you can focus your attention, for instance, to one of the grid cells. You can highlight it, and then you can see how is the threshold for a given time period for that particular grid cell. So you see here, do you have thresholds a bit below 4? This is just a conceptual example, but you have then some peaks corresponding to events or other factors that contribute to your capability. And of course, by having some sort of indicator for the timing, you can then at the same time get the actual map display of that particular time slot that you're interested in. Similarly, what is most important in the CTB context is what are the deviations from a baseline. You would like to see at what times are these detection capability lowered. So by just subtracting off a baseline threshold map, you can then see how much is your capability reduced at a given time. And in a similar way, you can run this sort of an animation for such a time interval. So now you see, to begin with, it's almost as normal. But as the time of the event occurs, you will see that there is an increase in or decrease in the capability. And just follow the numbers here. And if you get maybe 10-15 minutes after the event, most of the globe has a reduced capability by almost 1 magnitude unit. And in such situation, if you are interested, you need to turn to maybe other methods like correlation methods and other to investigate how perhaps your network can have a better performance if you're looking for particular effects during such periods. One of the input parameters to the calculation of the thresholds is the relation between the amplitude observed and the magnitude. And this has a quite high variance. This is an example for the DPRK 2017 test, where the estimated magnitude was 6.1. But if you look at the individual station magnitudes reported in the REB, you see that they have a quite high variability, and the standard deviations in these numbers are 0.35. So this, of course, we have to reflect when we calculate the probability of 90%. So in essence, we would like to have a lower variance in this estimate such that we can be more precise and have a better, more confident and lower estimate of the detection probability. But of course, this standard deviation is reflected in the calculation of the 90% thresholds. However, for a given source receiver path, we know that there are much smaller variability. If you take events in one region and one station, this correspondence has a much lower variability. This is an example for the NORSAR array, where we compare the NORSAR magnitudes with the IDC magnitudes. And you see here that the variability is much smaller, maybe having a variance of 0.1 or standard deviation of 0.1 instead of 0.35. And even this, we also mentioned that this first event in 2006 probably had a biased MB for the IDC, so the correspondence is very good when you consider a given source receiver path. We made a study in 2006 before the IMS network was fully operational. These were the stations that were available at that time. And we calculated the detection probability of the IMS network with calibrated magnitude distance relations. And at the time of the event, the KSRS was not operational, but we were able to get hold of 10 minutes of data. So you see for the network at that time, the detection probability of the IMS without the KSRS was about 3.8, but with KSRS data included, it's lowered maybe to 3.5. This peak corresponds to the actual event at the North Korean test site. However, you can also formulate the problem in a different way. By using available resources, you can say that what is the largest event that could have occurred during this time period. Then you use your best stations of the network to get this estimate, and this can be formulated mathematically. So what we did was to say, during this time interval, what could be the largest event that could have occurred at the North Korean test site with 90% probability? So if you go to maybe the last 15 minutes, from the available data, we could say that at the North Korean test site, there would be no event larger than 2.9 during that time period. But with including the KSRS station, it's probably lower down to 2.5. Similarly, we made a study in 1998 of the Novaya Zemlya test site, where we included the stations in Scandinavia. If you remember over the average properties, you see that the detection threshold for that area is estimated to 3.1, 3.2 for the IMS network. But by using a similar formulation, we found that for the stations that we have available real-time data, we could claim, maybe during a time interval with no events, that the upper magnitude limit of any possible event at that test site would be lower than magnitude 2. So this is a significantly different performance metric than the overall global average estimate. So this is something to consider, which can be readily implemented into the monitoring system. So summary, we believe that the potential of this method is not fully exploited and should be further developed. It is used as a key performance indicator, but it could also be extended. The method can provide estimates of the upper magnitude limit of events that could have occurred at the test site, which would be an interesting number for many state signatories. It will also call attention to time instances when a given threshold is increased, and then asking the operators to call attention to these intervals. And the method is not a replacement, but a supplement to current monitoring methods. We are ready to cooperate with PTS, and we have plans to communicate with them how this could be included into the re-engineered software that was presented earlier. And we believe also that this system should include graphical interfaces such that the NDCs themselves could derive the results on these statistics, both capability maps, temporal thresholds, and associated distributions. And finally, we have worked with the PTS to implement part of these animations on this OmniGlobe in the next by room. So please take a look and enjoy the animations. Thank you.
Thank you. We have time for questions. First you and then you, but we need microphones. Wait, I think can't hear. They can't record you. Right here.
The relative or the absolute?
Either one, doesn't matter. You say it's the Papua New Guinea earthquake, but it seems that everything is coming from the South Pole and then slowly works up.
Yes, we have had several comments on that, that sort of behavior. And you know, all these numbers are projected back to the origin time at the event. And you may think that for an origin time of 1715, the corresponding data at stations in Central Asia may be at 1725. So that means that an event close to the actual monitoring stations may influence the threshold at a distant point. So this is much like a side lobe effect you have in array processing, that you, given the kind of uneven distribution of the network, you would have this sort of effect. But have you had a regular pattern of stations, you would have avoid this. It's much like a side lobe effect you find in array processing.
I still don't understand how a station further away from the event would react.
I mean, what is known is that for the southern hemisphere, the best monitoring stations are in Asia, Australia, Europe. They're not in the southern part, in many cases.
Okay, we had another question right next to you.
Just curiosity, because you have done monitoring on Novaya Zemlya.
Yes.
And what about Franz Josef Zemlya?
Well, I mean, this method can be implemented on any site. The only important thing is that you have
But Novaya Zemlya belongs to Russia, yes? Or it is?
Yeah, we can monitor wherever we like.
You like?
Yeah. Everyone can monitor. In the CTBT context, you can see wherever you like. You look for events everywhere, yes.
No, because Franz Josef Zemlya was discovered by Austrian, and that's why I was.
Yeah, okay, yeah.
But I don't know if it's still.
It's Russia. Yeah.
It's Russia.
This is the former nuclear test site on Novaya Zemlya.
Okay, but you don't do monitoring on this complex of islands.
Excuse me?
You don't do any monitoring on this complex of islands.
Well, this was an example from 1998, a study we made. So all nations are, of course, free to monitor whatever sites they like.
Okay,
yeah.
Thank you.
Are there any more questions? Okay, can I ask that we have 3 poster previews, 1 minute each. And so if you're giving one of them, it's poster 7, poster 10, and poster 13. Please come up. Do we have the poster presenters in the room? Okay. 7, 10, and 13.
10, 13.
7, 10, and 13 is what's written here.
Doesn't matter.
Is it right? 7, 10, 13? Please, it will show.
So can I see the...
They bring it up there, so. Okay.
So good afternoon, everyone. Our poster is related to quantifying uncertainties in atmospheric modeling simulations resulting from different emission time resolution. We use around 200 sources with the best estimate from literature. We replace only 2 sources, but the strong one in northern hemisphere and the other one in the southern hemisphere with real reported releases. Do you want to know how much better the ATM predictions at the IMS stations get with this kind of input? Please come to see our poster. You will be surprised. Thank you.
There you go.
That's the poster?
Is that yours?
No, but that's the poster, not the preview. No. Ah. Well, there was a preview, but anyway. Okay, so it seems like it's displaying the poster, not the preview. But in any case, at the Commission, we have now empowered our technical units by upgrading the previously known as IDC Operations Center. So this is now the CTBTO Operations Center, and it's basically a one-stop stop that provides support for all technical teams. And as you see, there's a graph that shows multiple screens showing the different setups of monitoring tools that we use to control the incoming of data, the automatic processing systems. But now we have expanded further to check the infrastructure. We control the UPS power at the computer center, all servers, and as well as we have incorporated the Operations Support Center for the OSI. If you come to see our posters, you will learn a little bit about our concept of operations, as well as how the parameters and performance of the system are being used for monitoring the world for verification purposes. Thank you.
Thank you. So thanks to all of our presenters, and also thank you for attending the session. So you can go do your next session now.
Bon,
Good. Yeah. Okay.
I already know what to say on the first one. Huh?
Well, no questions. Yeah, I don't know anything about atmospheric transport models.
For that, skip it you. I tell him to write what he wants.
Yeah, that's right. So we're going to write something up now?
So it's not your session now?
No, my next one
Yeah,
is
we can do it now.
my next one's at 5:15. So 5:15, 3.3. Yeah, my next one's this one, 5:15. So
Yeah.
is there another session in here though?
Yeah.
Okay, so we have to go somewhere. Thank you.
I was so quiet.
Good job.
for the highlight, you have some, no?
Yeah, I have some meat. Yeah, but I need to send it
How long
before.
do you take?
Okay.
Try to after that. Done at 5.
We'll be here until 7.
Okay.
Okay. Okay. So you will sit with us, or? Yeah. Okay. It is continuation of yesterday's session, so we have only 2 presentations.
Review. Poster is
At 4:30. 4:30.
Yeah, so that's a different session. You know, only 2 talks now.
Yep.
Then lunch break. No.
Fantastic.
Yeah.
Is the same everywhere else?
I don't know.
Yes. No, he will not join.
But you said the poster was not after these talks.
Poster preview is 5:15. It is in front.
Poster preview,
It's not. So yeah.
we did yes.
So it's not after.
Yeah, but this
isn't-
is a continuation because they're
Yeah,
not
so-
all.
So we just do these 2 talks and then that's it.
Yeah, that's it. And we announced that the poster preview.
Okay. It's working.
Okay, so it's Brian, yeah. So, good afternoon, everybody. So now we continue this conference in this room with the continuation of the session that we started yesterday, atmospheric and subsurface radionuclide background and dispersion. So we have, for this session, we have 2 talks. Yeah. So we start with Brian Milbrath. We talk about the detection of argon-39 above underground nuclear explosions decades later as a signature. Please, Brian.
Hope it works. Ready? Okay, thank you. Good afternoon. Thanks for coming. As Anders mentioned, the title of my talk is The Detection of Argon-39 Above Underground Nuclear Explosions Decades Later as a Signature. And this work was done by myself and many of my colleagues at PNNL and also at the Nevada National Security Site, or NNSS. And the work I'm going to present today was part of a larger project called the Underground Nuclear Explosion Signatures Experiment Noble Gas Migration Experiment done at the Nevada test site. So noble gas detection is a cornerstone of nuclear explosion detection. That's why you hear a lot of talks about it. For a UNE, it is the noble gases that are most likely to escape to the surface and thus be detectable either in the atmosphere or the near surface soil. The reason that they're most likely is because they're gases, obviously, and because they're chemically inert, so they don't get bound up somehow. And several radioxenon isotopes are useful in IMS because they have strong fission yields, and the fact that there's several of them allows you to discriminate between nuclear explosions and other possible sources. Argon-37 is another CTBT relevant radionuclide. That is caused by activation as opposed to fission of calcium-40 in the matrix surrounding the nuclear explosion. And in all these cases, the argon and the xenon, these are short-lived radioactive noble gases that kind of align with the common desire to detect nuclear explosions quickly that this community is built on. So the noble gas migration experiments were a series of experiments conducted in chimneys at the NNSS where nuclear explosions occurred years ago. What we did in those experiments was we injected radioxenon and argon-37 and chemical tracers into those old chimneys, and then we did sampling in the boreholes and the shallow subsurface for months to study the migration of those gases. The purpose of that was to study how radioactive noble gases from UNEs transport through the surface. Also, we wanted to understand backgrounds and refine models. There was a heavily model component to that project. And the next talk after this one by Chris Johnson will provide a lot more information about this experiment. But the experiments were done at 2 locations on the Nevada test site. U-20AZ is a vertically emplaced UNE in the 20 to 150 kiloton range with a depth of burial of 686 meters, fairly large chimney up to about 175, and that's a welded tough geology. And in that test bed, a drill back hole to the chimney remained from the original injection. U12PO3 is a tunnel test bed where a number of low yield or less than 20 kiloton explosions occurred. The depth of burial there was much shallower, 261 meters because of the lower yields. But after that particular nuclear explosion occurred, a tunnel was drilled relatively close to the working point, only 60 meters away for a subsequent test. And so for that experiment, we drilled from that tunnel to the chimney. Next, please. Okay. Now, argon-37 is not an easy radioisotope to detect. And when I say that, sometimes that makes my colleagues mad because they're good at it. What I mean is it is not the same thing as what you might be used to, something that puts out gamma rays and you have a sodium iodide detector or germanium detector. It's not easy to detect because it has very low energy, 2.8 keV Auger electrons, or some combination of X-rays and electrons. And those are measured by using internal source proportional counters where you have the sample right in your counting mechanism. And that's a capability that was developed at P&L over a number of years, large effort in order to do that, and has led to the development of a prototype field system for analysis of such samples. And Jim Hayes on Friday will be talking about that argon field system pictured here, which we deployed at the Nevada test site for some part of our measurements. So anyway, so when we were setting up our experiment at U20AZ, we were looking for the background of argon-37. Argon-37 shows up at the 2 to 3 keV, but we had other stuff in it, unlike samples we had looked at previous. So we were not able to find often the argon-37. And so we were like, what is this? What is causing this? Took us a while to figure it out, chiefly by changing the gain on our detector, to determine that it was actually argon-39 that we were seeing at these old test sites. Subsequent to that, at U20AZ, we've done a bunch of measurements at the test site, and every time we've looked at a UNE, we see strong signals of argon-39. Now, background in air, argon-39 is 0.016 becquerels per cubic meter of an air sample, 0.016. So if you compare that with these numbers, U20AZ at the surface in shallow boreholes, 40 to 100 becquerels. Another chimney nearby, very strong, just like U20AZ. U2EZ was a location several hundred meters from other test locations where it was alluvial and not welded tough background. The U12P tunnel complex, we were seeing it in the tunnel air, even though that's a ventilated tunnel. We were seeing it if you took an air sample just standing outside of the tunnel, which is a big, huge opening the size of this room. We were seeing it certainly in the chimney. Even at taking a sample at the surface through a tarp, we were seeing very strong measurements of argon-39. And even if we grabbed an air sample just sampling the air right above, we saw a somewhat elevated argon-39. Now you compare that with measurements we've made at non-UNE sites. Again, according to the literature, and we've measured it ourselves, regular atmospheric air is 0.016 becquerels per cubic meter. We took some samples in the Cascade Mountains of Washington State. We saw that to 4 times higher. These are still much smaller numbers than you saw on the screen previously. Took some samples in Death Valley National Park down the road from the Nevada test site. Similar geologies, again, background levels. So, argon-39, I should have mentioned this earlier, argon-39 has a 269-year half-life. It is produced by neutron activation, just like argon-37, but it's potassium that is the capture isotope. This measurement has some implications. One is it does affect the sensitivity to detect argon-37, maybe not right away after a nuclear explosion, but a while after a nuclear explosion, just as we saw. Of course, we were a long time after a nuclear explosion. You're going to get interference and eventually not be able to detect the argon-37, even if there is still some present. But more importantly, so argon-39 appears to be easily detectable in the shallow subsurface. I'm talking, few meter depths at UNE sites for decades and beyond, for human lifetimes. It might be that argon-39 makes UNE detection easy for a long, long time. The signature of it's kind of like having a crater for visual folks. The signature of a UNE is there forever, or a very long time. It may even be that UNE detection is easier at later times than earlier times after the UNE happens. This is, of course, a very different way of looking at things from the way that we have been building up the CTBT capability for a number of years, where we've worried about observables that disappear quickly due to decay, dispersion, or possible concealment efforts. Argon-39 basically says the signature is there forever. Now, what it would not do is distinguish between UNEs that happened before and after a treaty signing. So if there were historical tests in the area, that's a problem as far as detecting new ones, at least with argon-39. And as an aside, it may be a useful way to detect if you have a number of tunnel adits to look at what's the appropriate ones. Further work is still needed. Much of this was kind of ad hoc on the sidelines of the larger noble gas migration experiment that Chris will talk about. We need to do dedicated measurement campaigns involving UNEs with published yields, different geologies, tunnel complexes that aren't currently being ventilated like the one we were at, chimneys not undergoing injection experiments like the ones that we were at. We also need a dedicated measurement campaign. I encourage others out there to measure backgrounds in non-UNE subsurface soils. And I'd like to ascertain how robust this signature that we have seen at every place we measured in the test site, how robust it is with time, yield, and particularly spatial extent from surface ground zero. How easy is it to find this signature? We've also not done a comparison of MDCs and backgrounds to compare it with other possible long-lived isotopes that might be out there. As a noble gas, it would certainly be near the top of the list, but we've not done that comparison. And that's my talk. Thank you.
Thank you, Brian, for this extremely important result. Questions and comments?
I'll ask the obvious one then. Why isn't the argon-39 migrating away, and is there a possibility that it's still being created?
Well, it's, of course, any time that would take activation, so that takes neutrons. So any current activity would be fairly small. And we've also done modeling efforts that seem to agree with the idea that once you've created it, it's a source for a really long, long time is what we've learned from our modeling efforts. But, yeah.
Could you comment on the cost of portable detectors of this isotope compared to 37?
It'd be the same. You basically just change the gain on your detector. We've actually, it's interesting, we have, I don't want to steal too much from Jim's talk on Friday. We have, so maybe he can talk about this more then, but we have designed, Jim's and his team at PNNL have designed the argon detectors to reach background levels of measurement. So that's the capability we've been working on for many years. These samples have been much hotter than background levels, and so they would not have needed to be, for at least for this application, they would not have needed to be quite so good. So whether there's much of a cost savings there, I don't know. But we actually, you know, the guys in the lab complain about how hot of samples we've been pulling and asking them to analyze.
I have one question. What about you? Okay, so you have argon-37 produced first also?
They're at the same time.
So
yeah.
what about the ratio between, and for how long can you measure that ratio, and can you use it for timing the explosion?
So the argon-37 is actually stronger than is produced at a larger yield and is stronger than the argon-39 for about a year. Now, I've seen a lot of plots that seem to imply that, well, you know, just due to the half-life after, you know, the thought in OSI thinking has been, you know, you need to get there fairly quick, and that argon-37 will pretty much be gone after 2 years. So doing a ratio between those two would be A, a new, it'd still be kind of a recent measurement. And there you're talking about trying to learn something between two activation products, which it's not the same thing as between two fission. There are some possibilities there. We are doing some thinking on that, but nothing so far.
Okay, so thank you again, Brian, for that. All right, so we go on with the next speaker, which is Christine Johnson. She'll talk about underground nuclear explosion signatures, the underground nuclear explosion signature experiment, phase 2, gas migration studies in a tunnel test location. Please.
Thank you everybody for coming to this talk. As Brian previously described, I'll be talking about the underground nuclear explosion signatures experiment, the second phase in particular. And we typically call this UNESI for short, so if I slip into the acronym, I apologize in advance. Before I dive into this, I'd like to just pause and make some acknowledgments to the many, many people who contributed to this project. It was a very large and complex experiment that involved a lot of people from both PNNL and the Nevada National Security Site. So in brief, the goal of the underground nuclear explosion signatures experiment was to learn about the radioactive gas transport around a historic, horizontally emplaced, in this case, underground nuclear explosion. And so here Brian was describing the P-tunnel entrance, and so that's what's shown here, with some of our large volume gas samples being pulled out of the tunnel. I won't go into too much detail with this, but I kind of wanted to step back and talk about what UNESI Phase 1 is, since I keep saying Phase 2. And so what this is was a series of noble gas migration experiments that took place in 2012 and 2016, where we injected 2 radioactive tracers and several stable gas tracers into a vertically in place test, the Barnwell test. And we saw a different series of results from these 2 experiments. The first one, both of the radioactive tracers were seen to be depleted when related to the stable tracer sulfur hexafluoride. But when we did the same or similar experiment in 2016, we did not see a depletion of argon-37. And when we went back and did further analysis, this seemed to be a result of pressurization that was done in 2012, about 6 months after the injection, where we pushed a lot of air into the chimney to try to force the samples to the surface much more quickly. And so we did not do this in 2016. We actually sampled for over a year and saw slightly different results from that. So if we move into UNESI Phase 2, this was done in the P-tunnel complex, U12P, and the injection was performed into the Disco Elm shot chimney, where Disco Elm actually occurred in September of 1989, and as Brian mentioned, it was fairly low yield, less than 20 kiloton nuclear test. And I'll show this same sampler diagram again in a few minutes. So what we injected was a pair of radionuclides along with a stable tracer. The radionuclides were xenon-127. That was chosen rather than this more standard xenon-133, xenon-135 series, because it has a much more favorable half-life for these type of long-term experiments at about 35 days. And then it was actually mixed at the source with argon-37, and there were approximately about 20 gigabecquerels of each of these isotope. And we injected them with a constant activity over time. It lasted about 4.5 hours. And before they were injected, they were mixed with the stable sulfur hexafluoride, or about 50 kilograms were injected at the same time. And you can actually see the injection borehole right here. And then I'll be mentioning in a moment the ventilation exhaust, and so that's what this large tube is. It actually is where the air comes out to ventilate the tunnel. So after we injected the tracers, we needed to actually sample for them. So this was done on 2 main locations. The first was in the tunnel, and then we also had sampling from the mesa, or the surface above the tunnel, in a borehole and from TARP samplers. So within the tunnel, we had 2 types of sampling devices. The first was a recirculating gas sampler. So essentially what this did was pulled air from a location, put it in front of a sodium iodide or cesium iodide detector in a gas volume, and then actually flowed that gas back into the location where it was pulled from to try to minimize the pressure changes due to the sampling. Within those, we also had small gas samples that were collected from the flow line for the recirculating gas samplers. And then also on that exhaust vent I mentioned on the previous slide, we took small 1 liter samples from that location as well. So one nice thing with the recirculating gas line is we were actually able to look at the xenon-127 evolution within the chimney without completely disrupting our experiment, since we were actually putting the gas back once we looked at it. And so that lets us actually get this interesting plot of activity concentrations in the chimney over time after the injection for about, I think this goes for about a month. And we can see here when we did our injection initially, we started out with a maximum concentration of about 580 megabecquerels of xenon-127 within that chimney gas. But after the injection ended, which is the red dotted line, you can see it drops off pretty quickly, both as a function of mixing with chimney gas and starting to spread out into the pore space in the surrounding rock volume. And we saw that drop down to an initial stable concentration of about 5 megabecquerels per cubic meter of air. And I actually put on here a decay line to show if decay was the only mechanism removing xenon-127 from the chimney, then it should have followed that trend. But we can see here that actually there had to be other mechanisms, transport mechanisms, potentially any small leaks that were also removing the xenon-127 from the system. And another note we noticed when we were going back and looking at this is we were wondering, what is all of this well above our detection limit before the injection occurred? And when we went back and actually looked at the timing, we realized this is when the sample containers actually were rolled past the detector, and then when they were sitting next to the detector prior to injection. So they gave off a pretty nice signal. So that was the first of the radio tracers. The second one we looked at was argon-37, as Brian previously mentioned. And one of the interesting things we did for the first time as part of this experiment was looked at the measurements of argon-37 on site rather than actually having to ship them back to the laboratory. So this made it much easier, much quicker for us to get results to determine do we have tracers in our sample or not. And this is the field deployable system that Jim Hayes will be talking about, I believe, on Friday, which is the system that allowed us to make these measurements on the Nevada National Security Site. And using this system, we saw that we actually detected our injected argon-37 in the P-tunnel ventilation, so that same ventilation stack I highlighted, pretty quickly after the injection. So we had to step back and wonder, could this possibly have been leakage from the injection borehole rather than immediate transit through the rock? We also had a second detector set up collecting samples in the reentry drift, which Brian mentions about 60 meters from the shot. And we did not actually see any argon-37 in that location. So that was the tunnel sampling. We also collected samples from the mesa and from a deep borehole that was drilled close to the chimney where we injected these gases. It was actually about, I believe, 80 meters away from surface ground zero where this borehole was drilled. And it was actually drilled to about 250 meters in depth, which is a little bit below where we injected the gas. And we completed this borehole with 4 gas sampling zones. So the way we actually completed these was to use porous material, so sand and gravel, to allow gas flow in the regions where we wanted to sample. And then we isolated each sampling zone from each other using a large amount of grout backfill. And from this large borehole, we actually collected over 200 samples, about 50 of which were very large volume, so 2 cubic meter samples, and the remainder were smaller 1 liter samples. We collected those large volume samples once a month, but we've seen from previous analysis that those large volume samples can actually disrupt the amount of gas flowing through the system. You can actually see large pressure dips and things like that in each sampling zone. So in between, we took only small volume 1 liter samples to get that better time discretization. So for measurements on Aqueduct Mesa from the borehole, looking here at again at the radio tracers that were injected. First, highlighting what Brian already mentioned, how argon-39 can act as a significant background when trying to measure argon-37. So in the deepest borehole zone we measured here, you can see the argon-39 signature was orders of magnitude above that argon-37 signature that we saw in the tunnel, essentially drowning out almost any chance we had of seeing the amount of argon-37 we injected, at least in early time. Then if we actually go over to the xenon-127, the most recent measurement we have data for is from October of last year. We're still processing the most recent samples. And if we compare that to a result that was taken from UNESI phase 1, it's a strong xenon-127 signal, versus phase 2 here, we can see that there's been no detection of xenon-127 in this borehole in any of the zones as of October of last year. So that was the injected tracers. If we go back and look at the argon-39, so that activation product from the historic UNE, we see a very different series of results, where if we go down to the deepest zone, the one closest to the historic test, we see over 20,000 becquerels per cubic meter of air. For comparison, typical atmospheric levels are 0.012 or 0.016 becquerels, so this is significantly elevated. And we can see the transport changes. If we move up to zone 2, it's slightly decreased, but then if we move into zones 3 and 4, which are much higher and also in different stratigraphic layers, we see a much larger decrease as we get farther away from the test. But actually, an interesting comparison is if we look at the mesa tarp, so very, very shallow, above surface ground zero, and compare it to a sample taken 15 meters deep, about 200 or 80 meters away, then we can see that there's a much larger concentration in that more horizontally similar location. And then we also took multiple atmospheric samples. These were staggered to make sure that they were taken before any borehole samples to try to minimize contamination from the borehole samples later. And we saw over 30 times the typical atmospheric levels, even just several meters above ground. So in summary, some of the major key findings here. First, that the natural transport mechanisms, so things like barometric pumping, diffusion, things like that, have not been sufficient to force transport of our injected tracers to the deep borehole from the injection point, at least in the 4 to 6 month period where we have results so far. Also, a key thing for future experiments like this, we've demonstrated the ability to use a much smaller volume samples, in this case 1 liter samples, for measurement of both the radioargons, so argon-37 and argon-39, and some of the stable gases that we injected. And finally, foot stomping, what Brian already talked about. Argon-39 is present in very significant quantities in the subsurface, even 30 years after an underground nuclear explosion. So this both serves as a long-term signature, but it also can impact our argon-37 detection limits. A few things that are still ongoing. I mentioned we still have a few large volume samples that are being analyzed for both xenon-127 and both of the radioargons. And we're also sending a few of our small volume samples, especially some of our most recent samples, which were collected in April of this year, and having a much higher fidelity analysis of some of the injected stable tracers, so freon and sulfur hexafluoride. So we're hoping that maybe this higher fidelity analysis will let us actually see some of our injected tracers. And finally, we're developing some models of both the argon-39 transport and the transport of our injected tracers in both a range of geologies and using a specific model of this P-tunnel complex in order to better understand the transport, or in this case, the little less lack of transport that we've seen. Thank you, guys.
Thank you very much, Christine. So, questions and comments? Yes?
Thank you, Christine, for your presentation. Jean-Elie from the University of Bern. So what I understood from your presentation is that decay nor transport mechanism can explain how the concentration of both xenon and argonaut decrease over time. That's right?
I wouldn't say that they can't be explained with a combination of those. So there's a large variety of transport mechanisms that it can explain the decrease. And just because we saw a decrease of xenon-127 in the chimney doesn't mean that it actually reached our sampling point yet, because if you talk about 80 meters and then start talking about spherical volume, there's a lot of pore space that gas could have diffused into long before we'd ever see it.
Okay, because for me that was a little bit unclear. Also, do you also have analyzed probably the water content of the soil, because it also might impact the transport mechanism from the borehole for the surface?
Yes, we know that the water content can have a significant impact. So especially if you start getting near the tunnel complex, that tunnel's been open and ventilated for decades. So it's actually dried out a lot of the rock. But the surrounding area is, I think, something like 97% saturated. So we know that the water can significantly impact that transport. And we're taking account of it when we start doing our simulations.
Thank you.
Any more questions? Yes?
Hello, my name is Austin Short. Just curious, how were you separating out the background that wasn't argon-39? Because you showed separate spectra for those, like a blue line and a black line.
So in this case, this is analysis that the argon analysis folks at our lab do quite often. Essentially, the efficiency measurement, the red line, is a scaled efficiency that they've had to do from a known sample of argon-39. So it's scaled based on the background, and then the background's something they collect before the actual analysis.
Okay, so thank you again, Christine.
Thanks.
So just before we end this session, we have an announcement. Jolanta, please.
Just a short reminder that we will have a poster preview for those of you who didn't have a chance to do this yesterday. There will be a poster preview in forum at 5:15. And the real poster session with people, we ask authors to attend the poster is at 4:30.
Okay.
And remember to vote. There will be a chance to vote for a poster preview. Still, there is ongoing open possibility of voting for posters and for oral presentations. Thank you.
Okay, thank you. So that's the end of the session. So I just declare it closed and thank both speakers again.
So we meet the 5 at the cube, the sauna cube.
Sure.
Around 5-ish. The sauna cube, the blue box at the entrance.
Sure. You haven't seen the cube. You must see the cube. At the exhibition, just the first one. When you
go down the stairs.
Yeah.
On this floor. When you enter, you go down a bit the stair.
Okay.
There are all the exhibition and the vendors.
Okay.
On the left,
There's
a blue cube.
Okay.
Sienta is there.
So we meet there at 5?
Yeah. Okay. I hope I'm done by then.
Yeah.
I don't know.
this on the floor. It's,
Really?
it's easy to
wants to start speaking between three of us. Otherwise, we're going to be looking at each other.
Yeah. Xavier has not hung it up yet. Yeah, that's right. The interview photos doesn't show that.
Do we share the role of calling the presenters?
As you wish. I mean, I'm not keen on doing that. If you want to do that, that's fine.
I don't mind doing that. Well, how do you want to? It depends who wants to start, really.
Yeah, we should decide, right?
Okay.
Why don't you start?
Okay, well, I'm happy to do that. And how do I pronounce your?
My name?
So we have to make sure that we're in time. Do you have?
It's 2:40.
Yeah. We have to start then.
Okay, we'll start.
2:40, yes.
Well, good afternoon, everyone. Welcome to Theme 3.2, Laboratories including mobile and field-based technologies. I'm here joined today with Robin Reedman and Nekeo Inoue, the two co-chairs. I'm pleased to introduce them, and also would like to thank the organisers of this excellent conference. We have 3 15-minute presentations and then 6 1-minute poster presentations in this session. And we're going to start with the first speaker, who will talk about the measurement of low activities of argon-37 by liquid argon scintillation, S. Pakimov. So I'd like to welcome him to give the first presentation.
Do you see Mr. this one?
Yeah.
Okay.
Good day.
Good afternoon.
It's a change. And pointer. Yeah. Good day. I present our work investigations of the characteristics of installation for the measurement of low activities of 37 argon based on the detection of liquid argon scintillations. It's our colleagues. I am present here Хлопин Radio Institute, St. Petersburg, Russia. One of the most significant evidence of violation of CTBT is the detection in the subsoil air elevated concentration of the argon-37, which is formed in large quantities during the interaction of nuclear explosion neutrons with calcium, which is a part of the rocks. The concentration of argon-37 retains higher value for much longer time than xenon radionuclides, so it is the ideal witness of the nuclear test. The local background concentration of argon-37 in the air depends on the location, proximity of nuclear facilities, the long time measurements near Bern in 7 to 12 years of our century shows a variation from 0.4 to 3 millibecquerels per meter per cubic meter. Registration of a concentration of more than 5 millibecquerels per cubic meter may indicate the fact of high neutron emission into the atmosphere. Traditionally, the measurement of argon-37 are carried out in the underground laboratory of Bern. Later, a low background counter was designed in PNNL, United States. Everybody knows these pictures. Lately, a mobile system, March the 2nd, intended for on-site inspection, was also developed. The volume of the proportional counter cannot be significantly increased due to the high content of argon in the atmosphere. The volume of equivalent air sample also cannot be significantly increased, which imposes a limit on the sensitivity and accuracy of the method. One of the possible solutions to the problem of increasing the sample volume is to convert argon to a liquid state. Due to the good scintillation properties of liquefied noble gases, and in particular argon, it is possible to measure the activity of argon-37 in the sample by registering directly the scintillation of the liquid argon itself. Here presented the decay scheme of decay of argon-37. It radiates OGA electrons with very small energy, 2.8 keV, the valence of the light emitted in liquid argon, 138 nanometers, is in the vacuum ultraviolet region, and its direct detection requires special PMT with magnesium fluoride windows or use of wavelength shifter as tetraphenyl butadiene. The yield of scintillation light of argon 40 photons per keV somewhat exceed even the emission of sodium iodide, 38 photoelectrons per keV, and in 4 times exceeds the output of organic scintillators. OGA electrons of argon-37 produce a high ionization density, which lead to a significant decrease in light output, up to 30–50% of the initial one due to ionization quenching. One of the critical moments is the narrow temperature range for the existence of argon in the liquid phase at atmospheric pressure from in this. In this range. Given that the temperature of liquefied liquid nitrogen at atmospheric pressure is near the region of argon, which is for 6.5 Celsius degree lower than the solidification temperature of argon. Adjusting the temperature of a sample of liquid argon in a range of about 3 degrees, quite a difficult technical task. However, if the pressure in the measuring chamber is increased by 105 bar, bringing the absolute pressure to 2.5 bar, the control range can be extended to 10 degrees. And the task of temperature control, state control, becomes more simple. The functional diagram of the installation for registration of liquid argon scintillation is shown in figure 9. Installation for recording, preparated gas and gas mixtures are in a cylinder 1-3 on a ramp. Cylinder 1 contains highly pure argon of brand 6.0 background gas. Cylinder 2 contains argon with the addition of argon 37, about 100 becquerels per liter. And cylinder 3 contains the same gas, but with the addition of pure xenon of brand 5.0 to a volume content of 1%. Using a simple gas system, the gas from the cylinders under a small excess pressure enters the detecting unit. The detecting unit it contains liquid nitrogen, without pointer. It contains liquid nitrogen reservoir, measuring chamber body, measuring chamber, vacuum gap, PMT, R331 of Hamamatsu, protective PMT container, liquid nitrogen supply, argon supply. The detection unit consists of a measuring chamber. It's a repeat. It's clear. The detection unit in a shield. The shield consists of passive lead shield, active scintillation shield, and thermal shield. The general view of detection unit and the general view of detection unit mounted on special table are shown on this slide. The technical requirements for this installation: minimal detecting concentration 8 millibecquerels per cubic meter has to be achieved. The active volume of liquid argon shall be around 100 cubic centimeter. Detection of at least 5 photoelectrons per decay of argon 37 also must be achieved. Light collection efficiency of at least 70%. Use of photomultiply tube with a quantum efficiency at least 20%. Investigation and possible use of wave length shifter like xenon or tetraphenylbutadiene with near 100% shifting efficiency. Oxygen and nitrogen contamination shall be in order of tens of ppm at maximum. The background count rate shall be 0.1 counts per second at maximum. Either active or passive shield of or a combination of both can be deployed. Use of electrically refined copper and aluminum parts. It's a PMT for this project. It's a Hamamatsu PMT R331. Of course, the optimal choice of PMT for building argon-37 scintillation in liquid argon installation would be a low-temperature photomultiplier with a window that is transparent to the ultraviolet radiation in equivalent of 127 nanometers, which provides high photon detection efficiency. However, attempts to occur with such a photomultiplier was not successful, and we chose Hamamatsu this PMT of Hamamatsu. And it is very good PMT because it's widely used in tritium installation, and the problem of tritium measuring is also difficult, and many similar moments. On this slide presented the results of simulation. Result of simulation for various quantity of photoelectrons emitted by photocathode of PMT. And as we have to provide 5 photoelectron registration, it's 5 here. It's a very good picture for registration, and as our estimation shows, it is possible to have 7 photoelectrons per decay of argon-37. At present, the work on the installation is not yet completed. In particular, the Cayenne analyzer has not yet been delivered. The main components of detection unit, including the measuring chamber with a volume of 100 cubic centimeter, manufactured. According to the revised plan, the study of the system characteristics will be carried out in the autumn. In accordance with the updated estimations, the installation will satisfy the required characteristics. Thank you very much.
In the interest of time, we'll move on to the next presentation, but thank you very much, Professor Packamov. The next speaker is Ashley Davis, who will speak about the higher sensitivity analysis of CT-BT relevant radionuclides. So I'd like to welcome him to give his talk. Thank you. Try and make up some time, that would be great. But do the best you can do.
Yeah, I will do. Good afternoon, and thank you for this opportunity. This presentation is looking at some work myself and my colleague Rich Britton from AWE did in collaboration with Jonathan Burnett and Harry Miley from Pacific Northwest National Lab in the US. And this is really looking at how perhaps laboratory measurements could help more in event analysis than what they're currently doing in confirming detections on the IMS. So conventional gamma spectrometry are done by all of the radionuclide labs and the stations. It's using a high-purity germanium detector, and you get a spectra where you've lost really all timing information of when that interaction happened in the germanium crystal. And if I was working in an environmental lab, how would I improve the sensitivities? Well, I would increase the measurement time, increase the sample time. Both of these things aren't available under using the current IMS stations. One of the other options is, as the detection limit is a product of the resolution of the detector, you could improve the resolution of the detectors, but this currently is probably at the maximum it is from the commercial available detectors. One of the other options is to pre-concentrate or do radiochemical separation. This also isn't allowed within the treaty. So the only thing really in our hand is to reduce the background. So most of the labs are using low background detectors, such as the picture in the top right-hand corner, using low background lead. And they're also using other techniques to reduce the effects of high-energy particles, such as cosmic veto shields, and some labs going underground. But one thing that you can do to reduce the background is gamma-gamma coincidence. So what do I mean by that? Well, that's creating a spectra from events that are defined by 2 or more gammas in a specific time window, normally on the region of microseconds. So what I'm actually looking at is detecting this. No, I can't. It's that button. It's detecting this transition from molybdenum-99. There's a gamma ray that's 739 keV that then goes to an energy level of 181 down to ground state. So if you're looking for that unique signature, you can get a very low background, very high sensitivity measurement. And to do this, you need to do list mode over what was the conventional spectra. So you record a file with timestamps of the energy that happens in multiple detectors. And this allows you to replay the experiment and sort of reanalyze it in multiple ways. And one of the ways we do that at AWE is we quantify the signals from this using our code called RIMA, which I think we presented at the last SnT conference. So I'm not going to go into that. So here's a couple of the systems. So that on the top left-hand side is a prototype that was developed at AWE to test GEANT4 modeling. And then we've got a system below that that's in our laboratory to look at trying to change various detector geometry configurations. But most of this work was done in collaboration with PNNL, and this is their system Advanced Radionuclide Gamma Spectrometer, ARGO, which is in their shallow underground lab. And it consists of 2 germanium detectors face-on, surrounded by 12 sodium iodide detectors. And for this work, those 12 sodium iodide detectors have been acting as a Compton shield. So how do we validate this? Well, we were at PNNL. They irradiated some uranium on their neutron generator, and then we measured that for 2 days, 44 minutes after irradiation. We used the tools that we developed in our laboratory to do the data acquisition, so all of the detectors, the 14 detectors, are on the same common time frame. And then we've developed tools based on C++ and Root that actually generates multiple histograms in various forms. And this also generates some pretty pictures, so you can see on the right-hand side the gamma-gamma matrix. And this work here was done for the Ruthenium-106 that was over Northern Europe, and I think Ian Hoffman's talking about this on Thursday. So this is how it works. We take all that list mode data and we recreate a spectra. So on the left-hand side, you can see the sum of the spectra. And then when we're going to do the coincidence, we set a gate. So we're going to set a gate around this 730 keV gamma line, and we're going to extract what's in coincidence, which is the 181. And you can see the 2 graphs there. One of them is using the Compton suppression, and one of them's without. And you can see, possibly, the baseline's being reduced by Compton scattered, gamma's being reduced. And if you look at the results we're getting, they're consistent with all 3 methods, so we know the technique works. It's not as simple as just taking a library. You've got to be very careful on what pairs you're using. So if you look at lanthanum-140, for instance, what you can see is our code prints out how many gammas are in cascade. So if you have more than 2, you could be vetoing those out of the spectrum. But what you notice here is the 815 projecting out the 1596 is actually in good agreement with the 925 and 867. And this is because 22% of the time that cascade happens with 2 gamma lines, and the 4 is only seen in 0.015% of the time. And if you see our poster, Rich Britton's poster, it shows you how we increase the efficiency of detecting the cascade. So instead of just doing one extraction and looking at the 1596, we can gate on all these gamma rays. So we're getting a much higher efficiency by adding all those up and getting a virtual peak. So what we were interested in was to see what the sensitivity was. The cesium-134 is not produced. So what we looked at was what was the MDA. On the complete spectra, it was about 100 becquerels. And then we reduced that down to 33 becquerels. And here you can see the typical background you've got, where you compare to the full spectra that had about 5,000 counts per channel, we're down in the region of about 10. And you can see on the left without the Compton suppression and on the right with the Compton suppression. So why would we go through all this effort? Well, I'm going to demonstrate two examples. One of them is a cesium-134-137 ratio that's seen at JPP38 after the Fukushima accident. So if you plot all the data from the IMS and you look at that compared to the source inventory of the Fukushima reactor, you can see that it's pretty well spread around the predicted lines. In fact, it's slightly in excess of cesium-137, so you could actually say that that's probably okay because that could be resuspension from Chernobyl or nuclear test debris. But if you zoom in and you look at some measurements we're getting now, and this bottom orange dot with a large uncertainty is a measurement on the IMS. So we're actually in excess of cesium-134. So that could actually indicate that we've got a fresh release of cesium-134. So this was sent to our lab. We run GBL15, which is a certified lab, and we measured this on our low background detector with a cosmic veto, and you can see in the insert there, this is where the cesium-134 peak is. So it's very close to a bismuth peak, and it's in the region where there's some structure from germanium activation from high-energy neutrons. So what we thought was, what would this look like if we actually used a gamma-gamma coincidence system? So here you can see the red dots now closer to the predicted cesium-134-137 ratio. And what you've got here is a different way of looking at it. You've got a very low background. So you've got about 15 counts, but in that region you've got no background whatsoever. So the gamma-gamma system's obviously giving you a lower detection limit, and it's bringing you closer to the predicted line. Again, why would we do that? Well, this is the one I want to show you, which is the barium-lanthanum detections in May 2010. So there are a number of hypotheses that have been put out that these lanthanum and barium detections were from. And I'm referencing a paper from Wright with some of these options. So one of them is that it was a prompt release from a undeclared North Korean test on the 11th of May 2010. The second one was it was a release from this Monju fast reactor that just started up in Japan. Or the third one is it was a release from the radioisotope production facility from research reactor in South Korea. So what I want to say is if states parties or NDCs could make requests on special event analysis, what would the actual benefit would be to these sorts of detections? So I've done forward modeling, and I'm not an ATM guy, so I've done forward modeling from each of these locations and looked at what the contribution would be at each station. So I've got three graphs like this. So the IMS detected 6 detections in JPP37. They didn't detect these in JPP38, but the model is predicting that they would have. But in total, you've got 8 detections on the IMS network. And then if you sent all of these station samples to the current radionuclide laboratories, you would only gain 1 other detection because the detection limit for barium-140 on the radionuclide labs is probably about half of what's on the IMS. But if we could send these to laboratories, have a system similar to the one at AWE and the one at PNNL, and there's also ones in France and Canada, you would actually be able to reduce the detection limit by an order of magnitude. So what this would give you an 18 detections. And perhaps more importantly, what it would give you would be 5 more stations. So when you're doing looking back for the source term, you've got much more inputs into your ATM models. So I go through the 3 scenarios. So this is Monju. It shows the same thing. You'd go from 13 detections on the IMS network to 33, and again giving you 5 additional stations to aid in location analysis. And then the final one is the research reactor in South Korea. Again, you've got 14 detections on the IMS, but you would get 31 using this advanced technique. So you get a lot more measurements and you get a lot more stations to help in location analysis. So really, to conclude, there are a number of advanced systems being developed, tested, and operationalized in a number of the radionuclide laboratories. And for us, we put a substantial effort into trying to understand this analysis of this high multiplicity coincidence systems. We've developed software now to acquire, process, and analyze large complex data sets, and that's now being used by 5 of the IMS laboratories. The CTBTO laboratories play an important role in confirming IMS detections and improving such things that do help in event analysis, such as the zero time. But these advanced systems have a potential to offer far greater detection capability, potentially doubling the number of detections and trebling the number of locations per event. So this existing advanced gamma spectrometry systems could be used in this special studies or this URR development production as the PTS tried to put procedures into how to implement that. Finally, I've just got a few references, including the one that I took for the atmospheric transport modeling by Wright, and the others on how we actually quantify the signatures using our code rimmer. So thank you very much.
If we have time, we'll take questions after all 3 presentations. So thank you, Dr. Davies. The next presentation will be by Michael Fox on sample throughput improvements for radio xenon analysis.
Thanks everyone for coming. So Ash talked a bit about the particulate labs. I'll talk a bit about the xenon labs for noble gas analysis and give some motivation of why we might care about sample throughput improvements. So one of the reasons, which I'll go into, is there's 16 particulate labs, and of those 4 have noble gas are certified for noble gas measurements. I'd like to also thank the various collaborators that have been involved in the production of the system, sample measurement, and throughput. So I'll give a brief overview of the current system that we have and how we process samples, what we use to process them, and then I'll go through a little bit of the motivation of why do we care about increased sample throughput, and how do we go about that specifically at USL 16. And finally, I'll go through a little bit about the detector calibration analysis of what we've done to try to bring our new detectors online. So USL 16, it's the system shown here on the right, which is used to take archive samples from the IMS stations, purify them down, and measure the radioxenon from that container and perform a validation measurement of either the station sample or possibly a QC spike. So there's various things that are included, that have to be included for a noble gas or a CTBT IMS laboratory, and so we've used those and are going to extend them onto the additional detectors for improved throughput. So the current detector that we have one detector as of now, is a double-ended beta cell with PMTs on both sides. It's about 6 cc's in volume, and that goes inside a slot within sodium iodides that are also then read out with double-ended, but a total of 4 PMTs for sodium iodides. And these are then gain matched during the initial calibration, and that's reproduced as we do cesium-137 QC checks. So the motivation for higher throughput, there's a variety of motivations, either in we get multiple samples when we have proficiency tests to certify is the capability of the laboratory, is it consistent from one year to the next, and is it what's needed for verification. There's also possibilities that we get multiple samples at once. Since there's only 4 labs compared to the 16 particulate, it's not uncommon that we might get multiple samples from a station all to one single laboratory. So it'd be nice to process those in parallel as quickly as possible. And then also there's possibility for a memory effect from calibration spikes from stations if they're validating new systems, such as the ones that are coming online, or looking at this next generation of Xenon International, Sana 3, SPAL XNG. So as they go through and do those station verifications, those could then be sent to the laboratories and be remeasured. Additionally, there's calibrating the detector. We want to recalibrate it on a semi-regular basis, and then PTE spikes. So some of these might be higher activities, some might be lower activities, but we want to be able to not have to go directly from a high activity sample to a low activity station sample. So we want to not miss what we're trying to see. So the two solutions that are possibilities are coated beta cells, which many of the new systems are going to, which solves the memory effect issue, but there's still the instance when multiple station samples come at once, you'd like to process them as quickly as possible. So for us at USL 16, we also looked at how do we bring multiple new detectors online at once. So we've decided that we should go to additional detectors, so convert our sample processing from a serial process to parallel processing. And this would also allow for measurement of the different samples so we can revalidate our results within the laboratory itself. So we're implementing 4 additional detectors at USL 16. They're a different design than the current one we have in operation. They're similar to what's going to be implemented in Xenon International with a sodium iodide well, with a plastic scintillator beta cell in the center well, and then each of those are read out with a single PMT. And so it's nice that we don't have to do gain matching, especially since we're not going to be doing, it might be an extended period of time between our samples at the lab, so it's nice to have reduce the potential for any variability within the detector. And this detector that we have here is about 4 cc's in size, so it's slightly smaller than the one we have currently. So that's something that we have to factor in as we bring those detectors online. So the setup that we have is, we call it the quad because there's 4 detectors kind of within the single shield. So we have each of the 4 sodium iodide wells and the beta cells sitting in those, all within the center copper shield surrounded by lead. And on top of that is the manifold that we use for gas injection and processing into each of the beta cells. So the next question is, what do we have to do to implement and integrate these new detectors into our current system without having a large impact on current operational status and methods? So a few of the things that we've had to do for the improvements, slightly smaller cells means we have to have a slightly smaller quantification volume where we measure how much xenon there is so that we ensure that we get enough into the beta cells. So for this, we had to get a new lower volume manifold that we use and we put on top of the detectors. There's also some plumbing that we didn't want to integrate everything into a single manifold and gas processing. So we have a line going from our sample processing manifold that we use currently to the new detector manifold where we can transfer all the xenon directly. And then we also wanted to retain the ability to recollect the xenon samples. I mentioned wanting to do revalidation of samples, being able to put it on a different detector from the different 5 that we'll have in store. And so we want to be able to recollect the sample without having to go back up to the top manifold. And so we have that as well. So this is the overview of what all we have for the initial processing manifold that we have in place that's certified. We put the archive bottle on. We measure how much pressure is in the archive bottle, and then we flow the gas through a cryotrap, which is cooled down with liquid nitrogen, and inside that we have metal springs, which serve to increase the surface area for the xenon to collect on. And we pump all the gas through with a roughing pump, and that gets rid of the nitrogen or helium that might be used as a carrier gas within the archive container, but allows us to retain the xenon volume. We then drop down this dewar, quantify the amount of xenon within this quantification trap and manifold using the MKS 910 sensor, so we can measure the pressure and then how much concentration of nitrogen and xenon there are in that sample. So after that's collected, we then push it down to this new lower detector manifold through a small peak tubing, but then using nitrogen to make sure that we push all of it down to the lower manifold. And we do that same quantification step down here with another 910, so we can make sure, so we know what our transfer efficiency is from the top processing manifold down to the quantification manifold for the lower detectors. And then finally, we just volumetrically transfer that gas into one of the new 4 beta cells. And then after that step is done, we would recollect what's left over, put it into the transfer tube so that we can hold it on site, and then go on to the next sample. So this is what the potential sample processing timeline would look like. So normally with just our current cell, we'd have a gas background that's counting before we get the sample in. We get the sample, we start processing it, do a QC count to verify that the energy calibration is consistent, and then we count the sample for 24 hours, and then we do a 24-hour gas background and go to the next sample. So overall, each sample would take about 2 days to process. With the addition of the 4 new detectors, they can all be counting backgrounds as well. And then we do a QC count. Since they share the same cave, we have to QC calibrate them all at once. And then we can start the processing of each of the next 4 samples. So it takes about 2 hours per sample. So we could theoretically get up to about 5, but generally it's on the order of 2 to 4 samples per day into the detectors. So there's a lot that goes on now that we have potential for 5 samples going in parallel. So we want to not have to have manual operation do that. We want to have as much automation as possible. So we currently had automation of the process to go through and do the quantification, do the injection into the beta cell. We've improved that to do parallel processing of the system and load each of the cells individually. So this is what it looks like where we have different states, different parameters, so we can say, okay, how long do we want to count? Do we want the gas background to be an hour? Do we want our sample measurement to be a day? Do we want to increase our sample measurement to 3 days, 5 days? Maybe we want to have a longer count for a low activity sample. So since the detectors they're not memory effect coded, also have potential kind of how do we utilize the new detectors? We have 5 detectors, but we want to try to target the different purpose from different detectors. So we have 2 new detectors that I say might be high activity, maybe they're used for calibrations, maybe they're used for the QC of stations. And then we can also keep 2 at lower activities where we don't know when the station samples will be coming in. If we knew when the events were going to take place, it'd be a lot easier, but that's not how it works generally. And so keeping those at low activity, we can then know that there's always something pristine and ready for a low activity or long duration count. And then also, we can alternate these detectors, so maybe if there's a period of duration where there's no samples for a long time, they all become low activity detectors again, and then we can swap those around so that we know that each detector is capable of both the high activity and the low activity measurements. So one of the things I mentioned, they're not memory effect coded, so we wanted to verify what was the memory effect. Does it compare well with the current detector that we've quantified? And it does. It's slightly lower, definitely quite a bit lower statistics for the current measurement, but it's in line with about the 3% that we've seen for the current detector. And so that will then be subtracted off as we do the 24-hour gas background in between measurements. So we've calibrated each of these 4 detectors now with the Xenon 131M, Xenon 133, 133M, Xenon 135, and then also radon. So we've got all those energy calibration interferences that we can take into account. One of the things that we also noticed is the new detectors are with the single PMT. They're better energy resolution than the 2-sided detector. So this is for the 133M. The energy is slightly pushed out in terms of the scaling, but it's definitely better energy resolution. So that allows us to have less interference from the metastables and perhaps allows us to improve our detection counting capabilities so that we can have broader regions and measure low activity samples. So just a few conclusions now that I've given you kind of the overview of what all we've done and what the current status is. So the Noble Gas Laboratories, as we move to higher utilization rate, it's important to make sure that we have the sample throughput that's needed and desired. So at USL 16, we're implementing 4 additional detectors to improve our sample throughput. The additional detectors have improved energy resolution, but they don't have the memory effect coding, so that's possibly something that we might go to in the future to have memory effect coded cells, or also as we move towards silicon, we could also further improve that energy resolution. And then with the improvements, USL 16 will then have the potential for processing 2 to 4 samples in a day with the additional detectors. With that, thank you for your time, and I'll take any questions.
I'd like to thank all presenters for their excellent technical contributions and for sharing their expertise with us. For those of you that do have questions, I would suggest you approach the presenters during the coffee break or later in the week, and I'm sure they'd love to speak to you about the great work you've just heard presented today. To summarize, we've had three presentations indicating three areas of potential technology innovation for CT-BT laboratories. We've heard about, these are argon-37 analysis for the on-site inspection laboratory, further reducing background in IMS particulate laboratories using the gamma-gamma coincidence technique, and enhancing the noble gas analysis capability by increasing sample throughput at IMS laboratories, as well as increasing sensitivity. So we, as the chairs, would encourage the community to start exploring the next generation of CT-BT laboratory techniques. And I now have the honor of handing over to Naoko for the poster session. Thank you.
So thank you very much. The next next one is poster preview. The authors of posters, could you come up to front as soon as right away? We should have 7 posters. I'm sorry? Can I read the number? Yes. Okay. We have. We would like to make a queue in order, in a sequence: poster P1, poster 2, poster 4, poster 5, and poster 7, and poster 9. Thank you very much.
For added accuracy in gamma spectrometry, correction for coincidence summing is highly desirable. And in this study, several radionuclide of CT-BTO IDC event screening for particulate sample which contain fission and activation products were analyzed looking at the summing coincidence effect. Now, these coincidence correction factors were computed and compared using LabSOX and the VGSL developed by the Radionuclide Development Unit for the IDC. Now, I would like to invite you to come and to visit our poster to find out if the LabSOX coincidence correction factors are identical or may be complemented by the VGSL factors. Thank you.
Hello? Oh, something awful's happened to that. The poster is much better quality than the slide. This is a project that we've been doing at GBL 15, where we are looking at some high-resolution beta-gamma coincidence spectroscopy. So we're using the PIPS box, which is in use on the new SPALAX NG, and we're hoping to develop a laboratory system for research purposes and also sort of future-proofing our noble gas capability in the UK.
So in Sweden, we do precipitation sampling by funnel and then passing the precipitation through an ion exchange column. And we have looked at the efficiency of these ion exchange columns for precipitation and found that the efficiency is really good for the most of the radionuclides. But we have problems then when we ash the content of the columns, and we have a great loss of iodine. So, thank you.
Good afternoon, I'm Mattias Aldener from Swedish Defense Research Agency. We made a poster on how we made the field system into something that you had to carry, that you can actually mount in a fight pod and just have it rapidly deployed during an OSI. I'll be happy to see you there and talk about the details. I'll be talking your ears off. But if you rather want to talk to someone pleasant, you can talk to Lindsay or Johan in the back. They'll be probably around the poster too. So I'll be happy to see you there. Thank you.
So, good afternoon. Here we are in Vienna, and we find ourselves in this wonderful city, and I think you can tell it is nice by the people you've met, by the coffee you've had in the cafes and the restaurants and bars. But how would you know if this city is still good going into the future? Well, you could come back periodically every couple of years and check. Well, what that really amounts to is quality assurance, and what our poster is discussing is how do you provide quality assurance to a remote detection station in the IMS, such as a noble gas station. So we've come up with a means to do this, and it's illustrated in the poster. That's a collaboration between Idaho National Laboratory and the Swedish Defense Research Agency. So please come and see us.
Good afternoon. My poster describes the way to establish xenon proficiency test exercises for the IMS laboratories, which is very important as a QA/QC program because it gives us the chance to review the laboratory capabilities. In the poster, we show the performance matrix and grading scheme which we tested for the last 2 years. One thing to mention about this is that we added the evaluation of radioxenon isotope ratios because that's important for discrimination among possible sources. We did 4 exercises in the last 2 years, and the results look very good. Please come to the poster and have a look. The last point is that we want to start with official PTs from 2020 onwards.
So we also recommend you that you can vote on the app, both on the posters and on the oral sessions, if I'm correct. Who has troubles with the app so far? I've known one person that has troubles with the app. What? So your answer is confusing so far. Is the app as well? All right. Well.
Okay, well, all that remains is to say thank you very much for your attention, and again, thanks to all the presenters for this session. Thank you. That's okay. I thought it's better if all 3 of us at least say so.
That's fine.
Thank you very much.
Thank you. I think the first talk went a bit longer than planned, but I never like to turn them off.
We perfectly keep the
Well, for nice bit of aircon there. We have one missing presentation, so I'm going to announce that at the beginning.
Okay, which one's that?
The MITO presentation. And do you want to introduce the first one, or shall I just get it cracking? Shall I just?
You can.
Okay, okay, excellent. What was the time looking like? 22?
So this is 3.3.
Yeah.
Okay.
Good afternoon, ladies and gentlemen. If we can settle down for the final session of the day, please.
From the poster preview, only one,
okay,
which is number 12.
We only have one poster, right?
Yeah.
So good afternoon, everybody. Welcome to the final session of today for this particular room. The title of this session is Remote Sensing, Satellite Imagery, and Data Acquisition Platforms. We have 3 oral presentations of 15 minutes each, plus 1 poster preview. At the beginning, could I please ask if they're in the room, the 3rd oral presentation, C-MITO, to bring their presentation forward, please, and provide it to the conference staff to my right over there. So if they could do that now, please, that would be most appreciated. So we'll start off this session. We have three very different presentations for you this afternoon. We'll start off with a presentation on the continuous and unattended spectroscopic operation and analysis with the Mirion data analyst. Okay, and that's going to be presented by, I apologize for the pronunciation, Tsikafus and colleagues from Mirion. So if they could come forward, please, for the first presentation. Thank you.
Thank you. Thank you for the floor. Okay. So, sorry, but Mr. Dickelfoots couldn't come for this Congress, so I'm Eric Tischenbach. I'm in charge of this presentation for Mirion. The subject is a continuous and unattended spectroscopy operation and analysis. This new system from Mirion is a data analyst. What is the data analyst, and what are the applications for the data analyst? So, what is this? The data analyst is a platform, neutral continuous spectroscopy software system, where we install an embedded spectroscopy software designed to run a variety of platforms for various solutions. So you have some example of platform, mainly under Linux, but also could be available under the standard Windows industrial computers. This is the continuous, so acquire and analyze spectra continuously. On the web UI, access data via USB, also wireless connection via browser. So that will be easy to communicate with this platform. Just open the browser and enter the TCP IP address to obtain directly the embedded software. So you have the data analyst platform, and what are the compatibility with this new platform? This is compatible with the MCA tube-based Osprey from Mirion and the links for the scintillator detector, diverse as the sodomidide, the cerium bromide, the lanthanide bromide detector, but also with the links with all the high purity germanium detector, even the specialty detector designed to, for the drilling or for other application. We have also compatible the JR1. This is the small CZT detector, 1 cubic centimeters, where the MCA is integrated in the housing, so it's a very small detector. We can also connect the echo gamma to have at the same time the dose rate around the systems. And we can connect also I/O input-output system for flow, for pressure, for different information. About the software, you have the embedded software. So this is the data analyst software. We have also the possibility to develop a specific application thanks to the software development kit. Okay. And we have also the data prospector, the Horizon software. This is the software running under Windows, where you will have the capability to, for Horizon, to store the data and to follow the systems. And the data prospector is mainly for data review and replay the acquisitions. And at the last time, we have a full compatibility with our laboratory software for high-resolution spectroscopy as Genie 2000 and Apex Gamma, where each user interface have the capability to save the spectrum in the CAM file format compatible with Genie 2000. So what are the key features for the data analyst? First thing, this is the Genie 2000 compatibility, and we developed also all the algorithms from Genie for this application. So all the users of Genie 2000 will be confident with the user interface, the new user interface embedded inside the data analysis. We are also compatible with efficiency curve performed by ISOCs. This is a continuous acquisition mode as MSS. This is for multi-spectrum scaling acquisition. Multiple simultaneous analysis workflow. So I have a slide to explain what's the workflow, what is the idea of the workflow. Display on communication alarm or on analysis results. We have several GPIO to trigger from analysis workflow. Okay. Input-output for additional sensor, as you saw, and we have also the GPS for the mobile instrument. If you need to map a ground or certain area, you can have the GPS information stored with each spectrum. So this is the main view for the data analyst web browser, where you have some alarm information. You have in the left part all the possibility to set the system, to set the workflow, to calibrate in energy and efficiency your system. You have also the dose and the rate meter, and just below the need results. Because the main goal at the end will be to analyze, to perform the spectroscopy analysis, to quantify and to obtain for the nuclide present in the spectrum, the activity and also the MDA. Okay. So you have the spectrum view. You have also the waterfall display. This is an overview where you have all the acquisition represent in this graph depending of the energy. So what is the continuous spectroscopy system? It has a workflow which will aggregate and analyze this data at preset interval. So as you see, we perform 1 second acquisition and save the spectrum, restart, save the spectrum, and so on. This is the main feature of this system, is always perform acquisition for 1 second and store the spectrum. With that, the user have the capability to design, to define the workflow. So what is the workflow? This is a certain time to obtain a certain statistics that will be depend of the count rate, and where the system, the user asks for the spectrum corresponding to this range time range. Okay? And after that, the system analyze automatically the spectrum and give the 1 point information about activity demanded. So the workflow, with this system, the user have the capability to design, to define several workflows, depending on the statistic, but also depending of an alarm. For example, if you detect an unattended activity, you can activate a specific workflow where the time count is, the time preset is more shorter, for example, to aggregate for 1 minute as the activity increased during this time. Okay, in the main view, you have also the view for the evolution of the activity, where you have some points created after each workflow. So each result after the workflow, where you have the possibility to, with the mouse, to select 1 count directly to obtain more information and show directly also the corresponding spectrum. Okay. As you see in this graph, you have a blue line. This is to compare the activity to the MDA for this nuclide. Okay. So the user have the capability to select the nuclide, of course, to obtain this graph. We have also the data replay. So this is, as you have 1 spectrum for each second, it will be easy to ask to replay the count, okay, with other parameters. If you are now interested by a specific nuclide, okay, you can define this nuclide and ask to obtain the evolution. You have also, as you see in the waterfall, in the waterfall view, with the mousse, you can ask to sum or to aggregate a certain quantity of spectrum corresponding to, for example, the increased activity in the view. Okay, so about the Windows data prospector software, this is the more important, not important, but more important software under Windows, where we have the capability to download all the count from the data analyst, okay, to replay the count, to obtain some more precise graph in terms of evolution. Okay. You have the capability to turn any combination of nuclide to compare. So as you see in the first graph on the top, you have the list of all the nuclide, and you can select which nuclide you want to appear in the graph, and the system will automatically show the corresponding graph inside the second windows. Of course, you have the filter for the time range, okay? And you have also the capability to export at the end the aggregate spectrum to Gini 2000 to store the spectrum or to reanalyze with more efficient tools as the interactive peak fit and the cascade summing correction if it's necessary under Gini 2000. The last one is Horizon. This is the supervisory software for the data analyst. This is an existing software to manage many other this type of system. You see, you have the same windows as the embedded software in the data analyst, but this software can manage several data analysts at the same time in different positions. If the data analyst is connected to the internet network, you will have the capability to have in real time all the information coming from to the data analyst, to the Horizon software. With all the software as the data analyst, the Horizon, and you have the capability to save the spectrum to Gini 2000 format, but also N42 on the JSON software, JSON format. So we have many different formats to save the spectrum and save the data. Horizon is also attached to the database, so it will be more easy to collect the information and store the results to the Horizon database for a more easy retrieve or data review. What are the applications for the data analyst? We have, of course, the spectroscopy stack monitor, the continuous spectroscopy monitor, and other applications. So the first one we designed, this is an existing system, we designed a system to stack release for the noble gas as the xenon. This system could be used in the medical isotope production facilities, NPP, of course, on research NPP, research reactor, of course. So this system is based on data analysis to manage the count. We designed also data analysis combined with portable shield. So based on the small GR1 CZT detector, we designed a small tungsten shield with several collimators depending of the count rate. So it's a very small and compact system with the tripod, so it's easy to deploy the system in front of the interesting object or tube and so on. And we provide also a Peli case to transport this system easily to the interesting system, to the interesting field. So you have an example where we use the GR1 with its shield for the coolant water measurement. So this is existing system on the real measurement with this system, where we have the capability to follow many nuclide at the same time and to detect interesting system. You have also, with this system, the capability to subtract the background automatically. So if you perform the background measurement without water inside the circuit, you can define the background and ask to the analysis system to subtract the background automatically during the count and during the analysis.
1 minute. 1 minute.
Yeah, it's finished. The other application of data analysis, we can imagine the water monitoring for effluent, for municipal water intake. You have also, with the conveyor, we have some asking from customer for the soil, for the concrete, crushed concrete, but also for the food. Why not? You can use also here for the mapping system, okay, with the moving system, where the GPS will be interesting to store the information inside with the spectrum. And of course, now with the drone, you can use, for example, the very small JR1 with the drone to perform some plumes on top of the chimney, for example, to perform the measurement. Okay, so that was a short presentation for the data analyst system. Don't hesitate to join us to the stand, where you can obtain more details about this system. Thank you.
Thank you very much. Since we only have one poster preview, I think we can take 1 or 2 questions right now, if anybody has any questions. Ricardo.
Hi. In the case of that drone that you mentioned with the probe, that there are some experimental testing on that?
Yes, we use the drone with other health physics system. So with the small box, the small platform, you can attach the G1 on the small platform to the drone. The weight is very, very low, and you can communicate directly with by Wi-Fi with the data analyst.
Okay, which is the weight of the probe?
The weight exactly, it depends on the box, the platform, but the weight for the detector is 64 grams. For the CZT detector, and for the box, I think it's close to 300 grams. I have one, so if I will have tomorrow on the stand. If you want to see the system, I will have it.
Okay, thank you.
One further question, possibly? No? Thank you very much indeed. Thank you.
So we have only one other talk, unless Jefter on Dieki is here with their talk? No? Okay, so our final talk will be the International Radiation Monitoring System, IRMIS, by Sanjoy Mukhopadhyay. I hope I got your name close enough. Close enough.
Thanks for coming to this presentation of International Radiation Monitoring Information System. My name is Sanjoy Mukhopadhyay. I work at IEC, Incident and Emergency Center at IEA, Vienna, Austria. We are co-located with CTBTO, so we see most of these people every day going to lunch and stuff. So I'm going to talk about this. Basically, it's a online database. If you keep a few things that I'm going to say before I start in your mind, the things then will follow. So at the aftermath of a radiological or nuclear incident or emergency, the best thing the accident state can do to ensure the safety and well-being of the population is to define and implement the public protective action. You know, how far the evacuation has to happen, which people need to be sheltered at what time, you know, what type of food product can be used, and which area should be avoided for traffic. This kind of protection action can be defined only by monitoring. So a glaring example is Fukushima. like it was a pressurized water reactor. On an accident, it was a trigger mechanism that 3-kilometer evacuation zone, right? You have to evacuate 3 kilometers. But after the data start pouring in from multi-agency, primarily from USA, they said that 3 kilometers is just not enough. So just by the push from the data monitoring data, radiation monitoring data, that evacuation zone was expanded almost as 10 times that diameter. So imagine the resource allocation goes like square of the distance you have increased it. So a factor of 10 means 100-fold resource allocation. So if you needed 10 buses to evacuate 3 kilometers, you need 100 buses to evacuate, and Japan agreed to it. It's a, so that's the power of monitoring I want to impress on you. The second thing is, during the Fukushima response time, we were getting data in all sorts of format. Like somebody would sell Excel data, somebody would send PDF files, somebody would send text files, somebody would actually send the map products to us, and we had to make sense out of it. So there was a very badly needed urgency to create a harmonized data product and data handling mechanism. So we went ahead and developed, along with the EC, European Communion, the International Radiological Information Exchange format. It's an XML-based format. It is readable both by human and machine. It's very beneficial. I can give you an allegory of a postal stamp. Like, you know, you use a postal envelope, you put your message there in the form of paper mail, and then you put the address of the addressee and your address, and it goes to the right person. XML is exactly kind of like that. And the data packages get enveloped with the address it is going to, where it is coming from. All these details are embedded. It is hard to tamper with. It's very inexpensive because you can jam pack 10 megabyte worth of data easily without any effort. So that's the two aspects I want to keep in mind that we have provided to give a platform where a large amount of routine monitoring data or emergency monitoring data can be gathered, shared with the member states. You know, we have 171 member states that we serve. So these member states can share their collected data with the neighboring countries, and there is a visualization aspect of it. We didn't want the system to be very complex. In the background of the system, there is a SQL server that runs, but it lets you query on the data. And most of the query, we wanted it to be in the visual form. We want it to be visually compelling so that the data will jump out at it. You don't have to be a very sophisticated scientific algorithm. You don't have to use those. You will just be, the data will be self-evident. And in order to do that, we harmonize the data in terms of how we present it. We use the operational intervention levels. That is, suppose you're measuring dose rate in microsieverts per hour. If you are a light water reactor accident scenario case, then there are very specific oils or operational intervention levels defined. Oil 1, that 1,000 microsievert per hour, above that you have to evacuate. So we color code that to be red. So you know all the red points, people have to be evacuated from that area. Then comes up to 100 microsieverts per hour. That would be the sheltering area for, if it persists for more than 25 hours, you should shelter people. Then it's 10 microsieverts, where you should watch the food and water in the system. And rest below 1 microsievert per hour, we call it background. Okay, with that understanding, how do I move this?
There's a pointer.
Oh, sorry. Yeah. So I'm from IC. IC is supposed to be the global international focal point of all radiological and nuclear emergency that we respond to. We coordinate the response. So suppose something happens in far away from Vienna, we will still be monitoring, and we will be the conduit of exchange of information. So you can think of us as a information exchange hub, like is very eloquently said by our Director General, that effective national and global response capabilities are essential to minimize the impacts from nuclear and radiological incidents. And we do that. So consider ourselves as the hub. So it's the global focal point of emergency preparedness and response for nuclear and radiological emergencies, irrespective of the cause. If it is a nuclear power plant failure like in Fukushima, we don't care. Or if it is a malevolent act at RDD, we don't care. We're ready to respond. So that's what IEC's background is. That's where we work out of. There are about 26, 30 people that work in our section. So we have 5 basic mandates. One of the most important thing, as I said, the information exchange. We are the international hub. Notification and official information exchange. Provision of public information to make sure that public understands if they're safe, and if not, what they have to do. So those are the 2 aspects we care about. The third point is highlighted here: assessment and potential emergency consequences and prognosis of possible emergency progression. Where is the data? What is the effect? What is the range? What are the isotope mixes? What is the extent of damage? How far did the plume go? Has the plume gone by? Is it safe to be not sheltered? So those kind of things we need to answer in a very quick. You realize the Chernobyl accident took place in April of 1986. Within 6 months, by October, November timeframe, 2 very major conventions were convened. One of them is the early notification of nuclear and radiological accidents, where if there is a transboundary plume by some reason in your member state, you have created a transboundary plume that is flying out to the neighboring countries. You are supposed to forthwith, that's quote unquote forthwith, supposed to report this time, location, the extent of damage, how much quantity, if you have an idea of release has taken place. So these are legal obligation to people that has signed off on these treaties. Yeah? So we take care of that actually happens. People can notify us. And provision of assistance for requests. So if you are in a nuclear accident, and even advanced countries like in Japan were under some kind of stress in order to respond to Fukushima accident. And we had requests for assistance, and we comply with them by matching the offerer with the request that is being made. Different things have to take into account: geographical location, proximity, financial viability, and above all, if the demand and supply match. So we do that. So if I had to say in one word what ERMIS does, it definitely supports the international treaty, the early notification of nuclear accident. It provides a mechanism for large amount of data quantities to be exchanged. You can see a lot of countries, because of Chernobyl, the central part of Europe had installed lots of radiation monitoring system. We get data from USA and Canada, and also recently Indonesia has joined in as a data provider. So we can show gamma radiation dose rate, isotope-specific ground deposition for 2 isotopes, cesium-137 and iodine-131, both air concentration and ground deposition we are capable of presenting in this data. And then it can be supplemented with radiation monitoring during an emergency. the member states, if they are already in the habit of providing us data during the routine, steady state, normal situation, it will come to second nature when it comes to an emergency that we can get the data at a more frequent interval. So I mentioned that everything is harmonized in terms of the oils, the operational intervention levels. And the member state can change at their will. If you want to be more stringent, if you want the limits to be lower, you can change them on your own. The whole data set will change accordingly, so that you don't have to think about it, where the relocation has to take place or where the food has to be embargoed and things of that nature. 3 minutes, okay, yeah, I have to move fast. So there are two types of data, routine and emergency data. Routine data comes from fixed monitoring station that are collecting data all the time. So we have two IP probes that goes out, and member state don't push the data, we pull it from them. So member state whitelists those two particular IP addresses, and we pick up the data. And that is the routine data, but in case of emergency, it's open up. You can even send us data in a particular Excel format. We're going to show it. So here I want to realize that it can be a support tool. Look at the bottom here. This one is red. At this point, IC is going to negotiate with the member state if they should actually increase this diameter of the evacuation zone to include that red zone in. And in the top place, you're confident that the public protective action that you have defined is working. It's all within. It's very stylized data, but one of the information we get is the time series information, and just looking at this, you can definitely say 1, 2, 3, 4, at least 4 release has taken place. It is an exercise data, so it's very, perfectly Gaussian and all, but that's how it should work. I mean, by exploiting the Hermes data, you can detect pre-releases. We don't want this to be called, for legal reasons, don't want to be called a EWS or early warning system, but that's what it is. There's some vehicle monitoring data during the emergency. The whole idea is that it doesn't matter how you collect the data should match all data should be harmonized, that they have the same value. It's the aerial measuring data. It is very powerful. It worked perfectly well in Fukushima. You have a very high stand-up distance, so there is no crew safety problem from radiation. One misconception is people think that the aerial measurement actually measures the aerial content. The plume has passed by, the deposition has taken on the is on the ground, and we are measuring the effect of the ground deposition. So that we have a shared visualization. Any technical analyst can share this visualization with however country member they want, and this data would be exchanged just as was shown. There are 3 sides. One is the Hermes real, that's where the real world data comes, that's where the accident data will go. Hermes training instance, which is kind of opaque, and you can use it on your own. Nobody else has to know. And then there is the exercise instance. If you, as a member state, want to set up an exercise, give us 1 week's time, we'll set up, including the data form, data type. I'm closing up. So far we have 39 member states that provide data and 42 member states that have provided the data contacts. We have a new feature, the validate IRIX. If you bring your data in the IRIX format already, it can incorporate those. So we have the new data type. I'll finish it here. This is the contact point. It'll come to me and a few other in our office. So that's what it is. It's a live online database. It can share data and visualize data. It's very handy in emergency response situation. That's it. Thank you so much for your patience.
Thank you very much. Good talk. Does anybody have a question? We have time for a question or two. I have a quick question.
Yes, please.
Do you have, since this was, it sounds like when Fukushima happened, you had to worry about data harmonization kind of on the fly.
Yes, we did.
Is the system you came up with, is it ready for the next such event?
We hope so. We truly hope so. We can handle, I mean, we have checked up to 100 plus simultaneous access.
Okay.
We checked this.
Can I follow on from that? So with my data fusion hat on, I'm thinking of an on-site inspection launch phase where we would face a similar situation, a lot of data being in different formats, some of it just prints, etc., being given to us. I can associate with the problems that you were talking about there.
Yes.
My question is really in terms of the platform that you're using. Can you tell us a little bit about the visualization platform in terms of the technology there?
So it basically, we have two sorts of query. You know, we can actually put the data in tabular form where you can query, you can set them up in order of ascending dose rate, or you can query on the basis of which NPP it is coming from. We have a NPP visualization. So suppose you see a plume type data, and then you click on NPP and actually power plant shows up here. So without ambiguity, you know that the data most likely is caused by that NPP. And so we have, I didn't show in detail, we have way of putting spatial cut on the data on visualization, as long as, along with that, with the time cut. So that makes it, all this time series was done that way. We first put a special cut on the, where the suspected high dose rate data were, and then you automatically takes you to a time scale where you're grabbing the two and you can choose a time scale and then look at the time series. And time series tells a lot, you know, as I said, like pre-release or actual release happening.
Thank you.
Thanks very much. So we just have one poster presentation, number 12. So the presenter, if they can come up. Or did the presenter go to dinner already? Nobody's here for poster 12? Then I think our session is over unless we have something else to say.
I know there are some very interesting posters out there for this particular session. So I would encourage you to go and visit those posters. They are there. I know they are. So please take time to visit those posters and enjoy the content on those. So thank you very much again for the two presenters, and we can draw this session to a close. Thank you very much.
And my watch just told me the voting for your favorite poster is open until 7:30 tonight. So view the poster and vote for your favorite. Thank you.
Hi.
I didn't come in at the beginning. What happened to this thing?
They were not there. They didn't attend.
They didn't come?
No.
They didn't come.
No.
That's too bad.
Yeah, we had a captain. Yeah.
Where are they from?
Kenya. We had no information at all that we triple checked. So.
That's why you came.
I'm sorry.
We announced
well, actually, it was a nice way to finish the session off by having something again, which was on remote sensing, which we really wanted to